Welcome to Learning Elastic Stack 6 by Pranav Shukla and Sharath Kumar, a course by Pact Publishing. I am Todd Heppenstall and I will be the presenter of this course. Pranav Shukla is the founder and CEO of Valens Data Labs, a technologist, husband and father of two. He is a big data architect and software craftsman who uses JVM-based languages. Pranav has diverse experience of over 14 years in architecting enterprise applications for Fortune 500 companies and startups. His core expertise lies in building JVM-based, scalable, reactive and data-driven applications using Java and Scala, the Hadoop ecosystem, Apache Spark and NoSQL databases. Pranav founded Valens Data Labs with a vision to help his companies leverage data to their competitive advantage. You can follow him on Twitter at Shukla81. Sharath Kumar MN is currently working as a big data architect at CA Technologies. Prior to this, he was working as an Elasticsearch solutions architect at Oracle. He has done his master's in computer science at the University of Texas, Dallas in the USA. He is an Elastic Stack advocate, and being an avid speaker, he has also given several tech talks in conferences such as the Oracle Code event. He is a certified trainer, Elastic certified instructor, one of the few technology experts in the world who has been certified by Elastic Inc. to deliver their official From the Creators of Elastic training. Let's look at the overview of the course. The first section is Introducing Elastic Stack and gives a brief introduction to all core components, shows where do they fit in the overall stack, and details the purpose of each component. It concludes with instructions for downloading and installing Elasticsearch and Kibana to get started. After that, the section Getting Started with Elasticsearch introduces the core concepts involved in Elasticsearch. Concepts such as indexes, types, nodes, and clusters are introduced. The viewer is introduced to the REST API for performing essential operations, data types, and mappings. The next section, Analyzing Log Data, lays the foundation for the motivation behind Logstash, the architecture of Logstash, and installing and configuring Logstash to set up basic data pipelines. Moving further, Analytics with Elasticsearch covers various types of aggregations with examples to gain fundamental understanding. It starts off with very simple to complex aggregations to get powerful insights from terabytes of data. Section Building Data Pipelines with Logstash builds on the fundamental knowledge of Logstash by transformations and aggregation-related filters. Also, Visualizing Data with Kibana covers how to effectively use Kibana to build beautiful dashboards for effective storytelling about your data. The final section, Building a Sensor Data Analytics Application, puts together a complete application for sensor data analytics with the concepts learned so far. This step-by-step guide will show you the Elastic Stack, covering all the components through interactive and easy-to-follow examples. It also includes handy tips. So, let's begin this journey together, and I hope to see you there. Hello everyone. Welcome to the first section of the course, Introducing Elastic Stack. Elastic Stack is a rich ecosystem of components serving as a full search and analytics stack. And Elasticsearch is at the heart of Elastic Stack, providing storage, search, and analytics capabilities. Now we will move on to the first video of this section that deals with what is Elasticsearch and why use it. First, let us define Elasticsearch. Elasticsearch is a real-time distributed search and analytics engine that is horizontally scalable and capable of solving a wide variety of use cases. At the heart of Elastic Stack, it centrally stores your data so you can discover the expected and uncover the unexpected. Elasticsearch is at the core of Elastic Stack, playing the central role of a search and analytics engine. Elasticsearch is built on a radically different technology, Apache Lucene. This fundamentally different technology in Elasticsearch sets it apart from traditional relational databases and other NoSQL solutions. Let us look at the key benefits of using Elasticsearch as your data store. They are schemaless, document-oriented, searching, analytics, rich client library support and the REST API, easy to operate and easy to scale. near real-time, lightning-fast, and fault-tolerant. Let's look at each benefit one by one. We will begin with schemaless and document-oriented benefit. Elasticsearch does not impose a strict structure on your data. You can store any JSON documents. JSON documents are first-class citizens in Elasticsearch as opposed to rows and columns in a relational database. A document is roughly equivalent to a record in a relational database table. Next benefit is searching. The core strength of Elasticsearch lies in its text processing capabilities. Elasticsearch is great at searching, especially a full-text search. Let us understand what a full-text search is. Full-text search means searching through all the terms of all the documents available in the database. This requires the entire contents of all documents to be parsed and stored beforehand. When you hear full-text search, think of Google search. You can enter any search term and Google looks through all of the web pages on the internet to find the best matching web pages. Another benefit is analytics. Apart from search, the second most important functional strength of Elasticsearch is analytics. Many organizations are running analytics solutions powered by Elasticsearch in production. Search is like zooming in and finding a needle in a haystack. Analytics is exactly the opposite of search. It is about zooming out and taking a look at the bigger picture. Rich client library support and the REST API. Elasticsearch has a very rich client library support to make it accessible by many programming languages. There are client libraries available for Java, C#, Python, JavaScript, PHP, Perl, Ruby, and many more. Apart from the official client libraries, there are community-driven libraries for 20+ programming languages. Additionally, it has a very rich REST, Representational State Transfer, API, which works on an HTTP protocol. The REST API is very well documented and quite comprehensive, making all operations available over HTTP. Another beneficial factor is that it is easy to operate and easy to scale. Elasticsearch can run on a single node and easily scale out to hundreds of nodes. It is very easy to start a single node instance of Elasticsearch. It works out of the box without any configuration changes and scales to hundreds of nodes. Unlike most traditional databases which only allow vertical scaling, Elasticsearch can be scaled horizontally. It can run on tens or hundreds of commodity nodes instead of one extremely expensive server. Near real-time is the next key benefit factor. Not all big data storage systems are real-time capable. Elasticsearch allows you to index thousands to hundreds of thousands of documents per second and makes them available for searching almost immediately. Proceeding with the next benefit, lightning fast. Elasticsearch uses Apache Lucene as its underlying technology. By default, Elasticsearch indexes all the fields of your document. Elasticsearch contributors have leveraged Apache Lucene to its best advantage, and there are other optimizations which make it lightning fast. Last but not the least, the next benefit is fault tolerant. Elasticsearch clusters can keep running even when there are hardware failures, such as node failure and network failure. In the case of node failure, it replicates all the data that was on the failed node to another node in the cluster. In the case of network failure, Elasticsearch seamlessly elects master replicas to keep the cluster running. In the next video, we will be exploring the components of Elastic Stack. Hi, welcome to the next video of the section, exploring the components of Elastic Stack. Let's begin this video with the components of Elastic Stack. The Elastic Stack components are shown in this figure. It is not necessary to include all of them in your solution. Some components are general purpose and they can be used outside of Elastic Stack without using any of the other components. The first component that we will discuss about is Logstash. It helps in centralizing event data such as logs, metrics, or any other data in any format. It can perform a number of transformations before sending it to a stash of your choice. It is a key component of Elastic Stack, used to centralize the collection and transformation processes in your data pipeline. Logstash is a server-side component. Its role is to centralize the collection of data from a wide number of input sources in a scalable way, and transform and send the data to an output of your choice. Beats is the next component. Let's learn about it in detail. Beats is a platform of open source lightweight data shippers. Its role is complementary to Logstash. Logstash is a server-side component, whereas Beats has a role on the client side. Beats consists of a core library, libbeat, which provides an API for shipping data from the source, configuring the input options, and implementing logging. There are many Beats components that have already been built by the Elastic team and the open source community. The Elastic team has built Beats including PacketBeat, FileBeat, MetricBeat, WinLogBeat, AudioBeat, and Heartbeat. Kibana is the visualization tool of Elasticstack, which can help you gain powerful insights about your data in Elasticsearch. It is often called a window into Elasticstack. It offers many visualizations including histograms, maps, line charts, time series, and more. Kibana also has management and development tools. You can manage settings and configure XPack security features for the Elasticstack. Kibana also has development tools which enable developers to build and test REST API requests. Now we are proceeding with another component, and that is XPack. It adds essential features to make Elasticstack production ready. It adds security, monitoring, alerting, reporting, and graph capabilities to Elasticstack. Another important component is security. The security plugin within XPack adds authentication and authorization capabilities to Elasticsearch and Kibana, so that only authorized people have access to the data and they see only what they are allowed to see. The security plugin works across components seamlessly, securing access to Elasticsearch and Kibana. The security extension also lets you configure fields and document level security with the licensed version. Monitoring. You can monitor your Elasticstack components so that there is no downtime. Also, you can monitor clusters, nodes, and index level metrics. The monitoring plugin maintains a history of performance so that you can compare the current metrics with the past metrics. It also has a capacity planning feature. Reporting. The reporting plugin within XPack allows for generating printable high-quality reports from Kibana visualizations. The reports can be scheduled to run periodically or on a per-event basis. Alerting is the next key component. XPack has sophisticated alerting capabilities that can alert you in multiple possible ways when certain conditions are met. It gives tremendous flexibility in terms of when, how, and who to alert. Alerting also provides a wide variety of options in terms of how alerts are sent. It can send alerts via email, Slack, HIP chat, and PagerDuty. Now let's look at the next component, that is Graph. Graph lets you explore relationships in your data. Graph can surface relationships among entities which share common properties, such as people, places, products, or preferences. Graph consists of Graph API and a UI within Kibana to let you explore this relationship. Under the hood, it leverages distributed querying, indexing at scale, and the relevance capabilities of Elasticsearch. The last component of Elasticstack is Elastic Cloud. It is the cloud-based hosted and managed setup of Elasticstack components. Elastic is the company behind the development of Elasticsearch and other Elasticstack components. Apart from Elastic Cloud, there are other hosted solutions available for Elasticsearch, including one from Amazon Web Services, or AWS. The advantage of Elastic Cloud is that it is developed and maintained by the original creators of Elasticsearch and other Elasticstack components. In the next video of this section, we will learn the steps to download and install Elasticsearch and Kibana. Hi, welcome to the last video of the section, Downloading and Installing. Now that we have enough motivation and reasons to learn about Elasticsearch and Elasticstack, let us start by downloading and installing the key components. We will begin this video by downloading and installing Elasticsearch and Kibana. We will install the other components as we need them on the course of our journey. We also need Kibana because, apart from visualizations, it also has a UI for developer tools and for interacting with Elasticsearch. First, let's begin with installing Elasticsearch. Elasticsearch can be downloaded as a zip, tar, deb, or RPM package. If you are on Ubuntu, Red Hat, or CentOS Linux, it can be directly installed using apt or yum. We will use the zip format as it is the least intrusive and the easiest for development purposes. To download the zip distribution, let's go to the official website of Elastic and click on the download option zip. You can also download an older version if you are looking for an exact version. Then we need to extract the files. In our case, we have already extracted the files. Now we will navigate to the command prompt and change the directory to the top-level extracted folder, as you can see here. In the command prompt, we will run bin/elasticsearch or bin/elasticsearch.bat command to begin Elasticsearch. After that, we will open this URL in our browser. Once that is done, you will see an output like this. Congratulations, you have just set up a single-node Elasticsearch cluster. Further, we will look at the step for installing Kibana. Kibana is also available in a variety of packaging formats, such as zip, tar.gz, RMP, and deb for 32-bit and 64-bit architecture machines. We will perform a few similar steps as installing Elasticsearch. So, to download the package for Kibana, we will go to this link, which is the official website. From here you can select zip or tar.gz distribution for the platform that you are on. As we are using Windows operating system, we will select Windows option. Once we have downloaded the zip or tar.gz package, we need to extract the files. As we have already done that, we will proceed to the next step. Then we will navigate to the command prompt and change the directory to the top-level extracted folder. Now, to initiate Kibana, we will run bin/kibana or bin/kibana.bat command. Next, open this URL in your favorite browser. It works! Congratulations! You have a working setup of Elasticsearch and Kibana. We have successfully downloaded and installed Elasticsearch and Kibana to begin the journey of learning about Elastic Stack. In the next section, we will be getting started with Elasticsearch. Hello everyone, welcome to a brand new section of the course. In this section, we will start our journey of learning about Elastic Stack, starting at the core of Elastic Stack, Elasticsearch. Before we start writing our first queries to interact with Elasticsearch, we should familiarize ourselves with a very important tool, Kibana Console. This is important because Elasticsearch has a very rich REST API, allowing you to do all possible operations with Elasticsearch. Kibana Console has an editor which is very capable and aware of the REST API. It allows for auto-completion and for the formatting of queries as you write them. In Section 1, Introducing Elastic Stack, we successfully installed Kibana and launched the UI at localhost 5601. As previously said, Kibana is the window into Elastic Stack. It not only provides insight into the data through visualizations, but it also has developer tools like the console that you can see here. After launching Kibana, you need to click on the DevTools link from the left-hand side navigation pane. The console is divided into two parts, the editor pane and the results pane. You can type the REST API command and press the green triangle-like icon, which sends the query to the Elasticsearch instance or cluster. Here we have simply sent the query GET. This is equivalent to the curl command that we sent to Elasticsearch for testing the setup, http localhost 9200. As you can see, the length of the command sent via the console is already more concise than the curl command. You don't need to type http followed by the host and port of the Elasticsearch node. Let's send this query. You can see the corresponding response here. Also, as you start typing in the console editor, you will get an auto-suggestion dropdown, as displayed here. So, now that we have the right tool to generate and send queries to Elasticsearch, let's continue learning the core concepts. The next video is about mappings and data types. Hi everyone, let's start with the second video, mappings and data types. It is important to understand the data types supported by Elasticsearch. Elasticsearch supports a wide variety of data types for supporting different scenarios where you want to store text data, numbers, booleans, binary objects, arrays, objects, nested types, geopoints, geoshapes, and many other specialized data types such as IPv4 and IPv6 addresses. In a document, each field has a data type associated with it. There are core data types which are string, numeric, date, boolean, binary, and range. In string data types, we have text and keyword. The text data type is useful for supporting full-text search for fields which contain a description or lengthy text values. These fields are analyzed before indexing to support full-text search. The keyword type enables analytics on string fields. Fields of this type support sorting, filtering, and aggregations. You can see the numeric data types in detail here. Byte, short, integer, and long. Signed integers with 8-bit, 16-bit, 32-bit, and 64-bit precisions respectively. Float and double. IEEE 754 floating point numbers with single precision 32-bit and double precision 64-bit representations. Half float. IEEE 754 floating point number with half precision 16-bit representation. Scaled float. Floating point number backed by a long and a fixed scaling factor. The date data type has date with an optional timestamp component capable of storing precision timestamps down to the millisecond. The Boolean data type is common in all programming languages. Next, binary data type allows the storing of arbitrary binary values after performing base 64 encoding. Lastly, you can see the different range data types. They define ranges of integers, floats, longs, and so on. Next, we have complex data types. The complex data types supported by Elasticsearch are as shown here. Array data type means arrays of the same types of instances. For example, arrays of strings, integers, and so on. Object data type allows inner objects within JSON documents. Nested data type is useful for supporting arrays of inner objects where each inner object needs to be independently queryable. There are other data types too. Geopoint data type allows the storing of geopoints as longitude and latitude. The geopoint data type enables queries such as searching across all ATMs within a distance of 2 kilometers from a point. Geoshape data type allows the storing of geometric shapes such as polygons, maps, and so on. Geoshape enables queries such as searching for all items within a shape. And the IP data type allows the storing of IPv4 and IPv6 addresses. The other topic of this video is mappings. To understand mappings, let's add another product to the product catalog. Copy and paste this example into the editor of your Kibana console UI and execute it. The result is updated as we have done this several times. As you can see, the product has many different fields, as it is of a completely different category. Yet, there are some fields that are common in all products. The common fields are the precise reason why all these documents are called products. The second step involves defining the mappings for the type of product. When the first document is indexed within a type that doesn't yet exist, Elasticsearch tries to infer the data types of all the fields. This feature is called the dynamic mapping of types. By default, the dynamic mapping of types is enabled in Elasticsearch. To see the mappings of the product type in the catalog index, execute this command in the Kibana console UI. You can request mappings of a specific type, all types within an index, or within multiple indexes. The response should look something like this. At the top level of the JSON response, catalog is the index for which we requested mappings. The mapping's child product signifies the fact that these are mappings for the product type. The actual data type mappings for each field are under the Properties element. As you can see, only price is of the float data type. Other fields were mapped to the text type. You can learn more about get mapping at this link. That's all for now. The next video will be about CRUD operations. Welcome to the video, CRUD operations. Elasticsearch has a very well-designed REST API, and the CRUD operations are targeted at documents. To understand how to perform CRUD operations, we will cover some APIs. Index API, Get API, Update API, Delete API. Let's start with Index API. In Elasticsearch terminology, adding or creating a document into a type within an index of Elasticsearch is called an indexing operation. There are two ways we can index a document: indexing a document by providing an ID, and indexing a document without providing an ID. Let's first see how to index a document by providing an ID. We have already seen this version of the indexing operation. The user can provide the ID of the document using the PUT method. The format of this request is PUT index type ID with the JSON document as the body of the request. Execute it and you will see the output response. Next, we will perform indexing a document without providing an ID. If you don't want to control the ID generation for the documents, you can use the POST method. The form of this request is POST index type with the JSON document as the body of the request. The ID in this case will be generated by Elasticsearch. It is a hash string as highlighted in the response. Next is Get API. The Get API is useful for retrieving a document when you already know the ID of the document. It is essentially a get by primary key operation. The format of this request is Get index type ID. Execute this. The response would be as expected. Then we have Update API. The Update API is useful for updating the existing document by ID. The format of an update request is POST index type ID underscore update with a JSON request as the body. The properties specified under the doc element are merged into the existing document. The previous version of this document with ID1 had price of $54.99. This update operation just updates the price and leaves the other fields of the document unchanged. This type of update means doc is specified and used as a partial document to merge with an existing document. There are other types of updates supported. The response of the update request is as shown here. Internally, Elasticsearch maintains the version of each document. Whenever a document is updated, the version number is incremented. The partial update that we have seen here will work only if the document existed beforehand. If the document with the given ID did not exist, Elasticsearch will return an error saying that document is missing. Let us understand how we do an upsert operation using the Update API. The term upsert loosely means update or insert. Update the document if it exists, otherwise insert a new document. The example uses doc_as_upsert to merge into the document with ID 3 or insert a new document if it doesn't exist. Execute this query. We can update the value of a field based on the existing value of that field or another field in the document. Proceeding further, we enter the command and add the ID and _update. Look at the response. The update uses an inline script to increase the price by 2 for a specific product. Scripting support allows for the reading of the existing value, incrementing the value by a variable, and storing it back in a single operation. Last API is Delete API. The Delete API lets you delete a document by ID. So enter this and execute. The response of the delete operations is this. This is how basic CRUD operations are performed with Elasticsearch. In the next video, we will create indexes and take control of mapping. Usually, you wouldn't want to let things happen automatically, as you would want to control how indices are created and also how mapping is created. We will see how you can take control of this process in this video. You can create an index and specify the number of shards and replicas to create. It is possible to specify a mapping for a type at the time of index creation. This command will create an index called catalog with 5 shards and 2 replicas. Additionally, it also defines a type called my_type with 2 fields, one of the text type and another of the keyword type. We will now move to creating type mapping in an existing index. A type can be added within an index after the index is created. The mappings for the type can be specified like this. This command creates a type called category with 1 field of the text type in the existing index catalog. Let us add a couple of documents after creating the new type. After a few documents are indexed, you realize that you need to add fields for storing the description of the category. Elasticsearch will assign a type automatically based on the value that you insert for the new field. It takes into consideration only the first value that it sees to guess the type of that field. When the new category is indexed with fields, the field is assigned a data type based on its value in the initial document. So, this is the mapping after this document is indexed. Next, we will update a mapping. Mapping for new fields can be added after a type has been created. Mapping can be updated for a type with the put mapping API. Let us add a code field, which is of the keyword type, only with no analysis. This mapping is merged into the existing mappings of the category type. The mapping looks like this after it is merged. Any subsequent documents that are indexed with the code field are assigned the right data type. This is how we can take control of the index creation and type mapping process and add fields after the type is created. Next, we will look at an overview of REST API. Let's begin with the next video, REST API Overview. Broadly, the APIs that deal with Elasticsearch are categorized into these types of APIs: document, search, aggregations, indices, cluster, and cat APIs. In this video, we will cover the common API conventions applicable for all REST APIs. All Elasticsearch REST APIs share some common features. They can be used across almost all APIs. We will cover these features: formatting the JSON response, dealing with multiple indices. Let us look at each item one by one. We will start with formatting the JSON response. By default, the response of all the requests is not formatted. It returns an unformatted JSON string in a single line. Passing pretty equal to true formats the response. You can see that here. When you are using Kibana Console UI, all responses are formatted by default. We will now deal with multiple indices. We will cover the listed scenarios when dealing with multiple indices within a cluster. Let's look at a query that matches all documents. The documents actually returned by the query will be limited to 10 in this case. The default size of the result is 10 unless it is specified in the query. This will return all documents from all indices of the cluster. The response is truncated to remove the unnecessary repetition of documents. Let's understand it. Took is the number of milliseconds taken by the cluster to return the result. Timed_out is false. This means that the operation completed successfully without timing out. _shards shows the summary of how many shards across the entire cluster were searched for successfully or failed. Hit contains the actual documents matched. It contains total, which signifies the total documents that matched the search criteria across all indices. The max_score displays the score of the best matching document from the search hits. The hits child of this element contains the actual document list. Next, we will search all documents in one index. This command will search for all documents, but only within the catalog index. You can have a look here. You can also be more specific and also include the type in addition to the index name. like it is done in this query. Now, searching all documents in multiple indexes. This command will search for all documents within the catalog index and an index named my_index. Here we got the not found message, but if we had created the index, we will get the output. Further, searching all documents of a particular type in all indices. This line will search all indices in the cluster, but only documents of the product type will be searched. This feature can be quite handy when you have multiple indices, each index containing the exact same type. This type of query can help you query data for that type from all indices. That's all for this section. The next section will be analyzing log data. Hello guys, welcome to another exciting section of the course, analyzing log data. In this video, you will be exploring Logstash, another key component of Elastic Stack, which is mainly used as an ETL, extract, transform and load, engine. Now we will move on to the first video of this section that deals with Logstash. Let's begin with what is Logstash. It is a popular open source data collection engine with real-time pipelining capabilities. Logstash allows us to easily build a pipeline that can help in collecting data from a wide variety of input sources and parse, enrich, unify, and store it in a wide variety of destinations. Next, we will take a look at how to install and configure Logstash on your system. Let's take a look at the prerequisites. Java runtime is required to run Logstash. Logstash requires Java 8. Make sure Java_home is set as an environment variable. To check your Java version, you can run this command. On executing the command, you will see this output. For Java, you can use the official Oracle distribution, which you will find at this link, or an open source distribution such as OpenJDK. For that, you can browse to the official website of OpenJDK. Moving ahead with downloading and installing Logstash. Just like the other components of Elastic Stack, downloading and installing Logstash is pretty simple and straightforward. So let's navigate to this link. And depending on your operating system, you can download the zip or tar file as you can see on the screen. Currently, as we are working on the Windows operating system, we will download the zip file. Unlike Kibana, which requires major and minor version compatibility with Elasticsearch, Logstash versions starting from 5.6 are compatible with Elasticsearch 6.x. The compatibility matrix can be found at this URL. Now, let's unzip the downloaded file. Once unzipped, we will navigate to the newly created folder. Before that, we will clear the screen and then navigate to the folder named Logstash 6.2.4. The Logstash installation folder will be referred to as Logstash_home. Logstash requires configuration to be specified while running it. Configuration can be specified directly as an argument using the -e option by specifying the configuration file using the -f option or flag. Using command prompt, we will navigate to the bin folder under Logstash_home directory. Let's ensure that Logstash works fine after installation by running this command with a simple configuration, that is, the Logstash pipeline as a parameter. Once it is executed, we will get to see this logs as an output. Now enter any text and press enter. In our case, we have added hello and pressed enter. Here, Logstash adds a timestamp and IP address information to the input text message. Lastly, exit Logstash by issuing a Ctrl+C command in the shell where Logstash is running. We just ran Logstash with some simple configurations, that is, pipeline. In the next video, we will be discovering Logstash architecture and overview of Logstash plugins. Hi friends, welcome to the next video of the section, Architecture and Overview of Logstash plugins. Let's explore about Logstash pipeline and its architecture in detail. The Logstash event processing pipeline has 3 stages. They are inputs, filters, and outputs. As you can observe in this figure, a Logstash pipeline has two required elements: input, output, and optionally, filters. Inputs create events, filters modify the input events, and outputs ship them to the destination. Inputs and outputs support codecs which enable you to encode or decode the data as and when it enters or exits the pipeline, without having to use a separate filter. Logstash uses in-memory bounded queues between pipeline stages by default, input to filter and filter to output, to buffer events. If Logstash terminates unsafely, any events that are stored in memory will be lost. To prevent data loss, you can enable Logstash to persist in-flight events to the disk. Hi friends, welcome to the next video of the section, Architecture and Overview of Logstash Plugins. Let's explore about Logstash Pipeline and its architecture in detail. The Logstash event processing pipeline has three stages. They are inputs, filters, and outputs. As you can observe in this figure, a Logstash pipeline has two required elements: input, output, and optionally filters. Inputs create events. Filters modify the input events, and outputs ship them to the destination. Inputs and outputs support codecs which enable you to encode or decode the data as and when it enters or exits the pipeline, without having to use a separate filter. Logstash uses in-memory bounded queues between pipeline stages by default, input to filter and filter to output, to buffer events. If Logstash terminates unsafely, any events that are stored in memory will be lost. To prevent data loss, you can enable Logstash to persist in-flight events to the disk by making use of persistent queues. The Logstash pipeline is stored in a configuration file ending with a .conf extension. These are the three sections of the configuration file: input, filter, and output. Each of these sections contains one or more plugin configurations. A plugin can be configured by providing the name of the plugin and then its settings as a key-value pair. Let's save the file and enter the file name as example.conf. This file is created just for the reference purpose and will not be using it further. Now let's use the same configuration with some little modifications and store it in a file. First we will create a conf folder under logstash_home directory. Under the conf folder, we will create a file called simple.conf. It's good practice to place all the configurations in a separate directory either under Logstash Home or outside of it, rather than placing the files into the bin folder of Logstash Home directory. In this file, we will add simple Logstash configuration. As you may notice that this file contains two required elements, input and output. And the input section has a plugin named stdin, in which accepts default parameters. The output section has an stdout plugin which accepts the Ruby debug codec. stdin is used for reading input from the standard input, and the stdout plugin is used for writing the event information to standard outputs. The Ruby debug codec will output your Logstash event data using the Ruby Awesome Print library. It also contains a filter section that has a mutate plugin which converts the incoming event message to uppercase. Save this file. Further, we will run Logstash using this new pipeline or configuration stored in the simple.conf file by executing this command. Once Logstash has started, enter any input, say Logstash is awesome, and you will see this response. As seen here, along with the input message, Logstash automatically adds the timestamp at which the event was generated, and information such as the host and version number. The output is prettily printed due to the use of the Ruby debug codec. The incoming event is always stored in the field named message. Further moving on to overview of Logstash plugins. Logstash has a rich collection of input, filter, codec, and output plugins. Plugins are available as self-contained packages called gems and hosted on this website. By default, as part of the Logstash distribution, many common plugins are available out of the box. Let's navigate to Command Prompt and verify the list of plugins that are part of the current installation by executing this command. It results in the list of plugins. Using the double-group flag followed by either input, filter, output, or codec, we can find the list of installed input, filters, output, codecs, and plugins respectively. Let's take an example and execute this command to list the group filters. This way you can list down the group filter using the simple command. Also, we can list all plugins containing a name fragment by passing the name fragment to Logstash plugin list. Let's understand it well with this command. As you can see, all the plugin with keyword pager will be displayed in the result. Let's explore the steps for installing or updating plugins. If the required plugin is not bundled by default, one can install it using the bin/logstash plugin install command. For example, to install the Logstash output email plugin, we will execute this command. As the command is executed, the installation will begin, and on completing, installation successful message will be displayed. Using the bin/logstash plugin update command and passing the plugin name as a parameter to the command, we can get the latest version of the plugin. Let's have a look how we can do that with an example. We will run this command and observe the desired output. As you can see, the name of the plugin is passed and resulted with the status updated along with the version. Now let's look at the input plugins. An input plugin is used to configure a set of events to be fed to Logstash. The plugin allows one to configure single or multiple input sources. It acts as the first section, which is required in the Logstash configuration file. Details of each of these plugins and the list of other available plugins that are not part of the default distribution can be found at this web link. Moving ahead with output plugins. The output plugin is used to send data to a destination. Output plugins allow one to configure single or multiple output sources. It acts as the last section, which is required in the Logstash configuration file. You can visit this website for more details of each of these plugins and the list of other available plugins that are not part of the default distribution. Next is the filter plugin. It is used to perform transformations on the data. It allows you to combine one or more plugins, and the order of the plugins defines the order in which the data is transformed. It acts as the intermediate section between input and output, and it's an optional section in the Logstash configuration. Again, the details of each of these plugins and the list of other available plugins that are not part of the default distribution are available at this URL. Last plugin is codec plugins. These plugins are used to encode or decode incoming or outgoing events from Logstash. Codecs can be used in input and output as well. Input codecs render a convenient way to decode your data before it even enters the input. Output codecs provide a convenient way to encode your data before it leaves the output. Visit this web link for details of each of these plugins and the list of other available plugins that are not part of the default distribution. In the next video, we will be exploring input plugins and its types. Hello everyone, welcome to the new video of the section, Exploring Input Plugins. Let us walk through some of the most commonly used input plugins in detail. We will begin with File plugin. It is used to stream events from files line by line. It works in a similar fashion to the tail of Linux or Unix command. For each file, it keeps track of any changes in the file, and the last location from where the file was read only sends the data since it was last read. It also automatically detects file rotation. This plugin also provides the option to read the file from the beginning of the file. The location of since.db file is by default set to path.data, plugins, inputs, file, which can be overridden by providing the file path for the since.db_path plugin parameter. The only required parameter for this plugin is the path parameter, which accepts one or more files to read from. Let's take some example configurations to understand this plugin better. For that, first we will create a new file and name it as simple1.conf. Here we will add this code snippet and understand its functionality. The preceding configuration specifies the streaming of all the new entries, that is, tailing the files, to the files found under this highlighted location. After that, we will create another file and name it as simple2.conf. In this newly created file, we will add this block of code and understand it working. In this part of the code, it specifies the streaming of all the log entries or lines in the files found under the specified location, and only files of the .text type. Files found under this location, starting from the beginning as specified by the parameter start position as beginning, and while looking for files it excludes files of the .csv type, specified by the exclude parameter, which takes an array of values. Every line streamed would be stored in the message field by default, and the preceding configuration also specified to add a new additional field type with the app logs value as specified in this line of code. Adding additional fields would be helpful whilst transforming events in filter plugins or identifying the events in the output. The Discover Internal parameter is used to define how often the path will be expanded to search for new files created inside the location specified in the path parameter. Let's save this file. Next plugin is JDBC. This plugin is used to import data from a database to Logstash. Each row in the results set would become an event, and each column would get converted into fields in the event. Let's see an example, and for that we will create a brand new file named jdbc.conf. Here we will add this configuration and save this file. Using this plugin, one can import all the data at once by running a query, or one can periodically schedule the import using a cron syntax. When using this plugin, the user would need to specify the path of the JDBC drivers appropriate to the database, and the driver library can be specified using the JDBC driver library parameter. The SQL query can be specified using the statement parameter, or can be stored in a file. The path of the file can be specified using the statement file path parameter. One can use either statement or statement file path for specifying the query. In our case, we have used statement. It is good practice to store the bigger queries in a file. This plugin accepts only one SQL statement and multiple SQL statements aren't supported. If the user needs to execute multiple queries to ingest data from multiple tables or views, then the user needs to define multiple JDBC inputs. That is one JDBC input for one query in the input section of Logstash configuration. In our case, we have used schedule parameter to specify when to periodically run statement using cron syntax. The results set size can be specified by using the JDBC fetch size parameter. The plugin will persist the SQL last value parameter in the form of a metadata file stored in the configured last run metadata path parameter. Upon query execution, this file will be updated with the current value of SQL last value. This value is used to incrementally import data from the database every time the query is run, based on the schedule set. Parameters to the SQL statement can be specified using the parameters setting, which accepts a hash of the query parameter. This configuration is used to connect to company schema belonging to MySQL DB and is used to pull employee records from the IT department. The SQL statement is run every 30 minutes to check for new employees. Created since the last run. The fetched rows are sent to Elasticsearch and configured as the output. That's all about the input plugins. The next video is about the output plugin. Hi, welcome to the last video of the section, Output Plugins. Let us walk through some of the most commonly used output plugins in detail. We will begin with Elasticsearch. This plugin is used for transferring events from Logstash to Elasticsearch. This plugin is the recommended approach for pushing events or log data from Logstash to Elasticsearch. Once the data is in Elasticsearch, it can be easily visualized using Kibana. This plugin requires no mandatory parameters, and it automatically tries to connect to Elasticsearch, hosted on localhost 9200. Let's create a new conf file and name it as elasticsearch1.conf. The simple configuration of this plugin would look like this. Then we will save this file. Often, Elasticsearch would be hosted on a different server, usually secured, and we might want to store the incoming data in specific indexes. Let's see an example of this. For this example, we will create another file under conf folder and name it as elasticsearch2.conf. Here we will add this code snippet and save it. As seen in this code, incoming events would be stored in an Elasticsearch index named company as specified using the index parameter under the employee type as specified using the document type parameter. Elasticsearch is hosted at this address as specified using the host parameter, and the user credentials of Elasticsearch are elastic and elastic password as specified using user and password parameters respectively. If the index is not specified by default, the index pattern would be logstash with this format, and the document type would be set to the type event if it existed. Otherwise, the document type would be assigned the value of logs or events. One can also specify the document type index and the document ID dynamically by using the syntax percentage along with the field name. In the hosts parameter, a list of hosts can be specified too. By default, the protocol used would be HTTP if not specified explicitly while defining hosts. Next is CSV. This plugin is used for storing output in the CSV format. The required parameters for this plugin are the path parameter, which is used to specify the location of the output file, and the other required parameter is fields, which specifies the field names from the event that should be written to the CSV file. If a field does not exist on the event, an empty string will be written. Let's see an example. For this example, we will create a new file under conf folder of Logstash project. Name this file as csv.conf. Then we will add this code snippet and understand its function. So, in this configuration, Elasticsearch is queried against the Apache logs index for all documents matching the status code as 200, and the message at timestamp and host fields are written to a .csv file. Before moving ahead, save this file. Further moving on to codec plugins. Here we will take a look at some of the most commonly used codec plugins in detail. The first codec plugin is JSON. This codec is useful if the data consists of .json documents, and it is used to encode, if used in output plugins, or decode, if used in input plugins, the data in the .json format. If the data being sent is a JSON array at its root, multiple events will be created, that is, one per element. Let's look at the working example of JSON. For that, we will create a new file and name it as json.conf. Then add these JSON documents, and it is used to encode if used in output. Let's look at the working example and add these few lines of code. The simple usage of a JSON codec plugin looks like this. Make a note that if there are multiple JSON records and those are delimited by /n, then use the JSON_lines codec. If the JSON codec receives a payload from an input that is not valid JSON, then it will fall back to plain text and add a tag JSON parse failure. Next, we will look at another codec plugin, Ruby Debug. This codec will output your logstash event data using the Ruby Awesome Print library. For looking at the code example, we will create a new file and name it as rubydebug.conf. The simple usage of this codec plugin will look like this. Going ahead with the next plugin, Multiline. This codec is useful for merging multiple lines of data with a single event. This codec comes in very handy when dealing with stack traces or single event information that is spread across multiple lines. To observe the sample usage, we will create another file and name it as multiline.conf. In this file, we will add this block of code and understand its functionality. That's all about the output plugins. In the next section, we will learn about analytics with Elasticsearch. Hello everyone, welcome to the next section, Analytics with Elasticsearch. In this section, we will understand how Elasticsearch can serve as your analytics engine. We will start with the basics of aggregations. In contrast to search, analytics deals with the bigger picture. Searching addresses the need for zooming in to a few records. Analytics addresses the need for zooming out and slicing the data in different ways. While learning about searching, we use an API, so let's see that. Create a new file, basics.txt. This is the API. All aggregation queries take a common form. Let us understand the structure. All aggregation requests take this form. The aggregations or AGS element allows us to aggregate data. The AGS element should contain the actual aggregation query. The body depends on the type of aggregation we want to do. We will cover these aggregations in this section. The optional query element defines the context of the aggregation. The aggregation considers all of the documents in the given index and type if the query element is not specified. If we want to limit the context of the aggregation, it can be done by specifying the query. The size element specifies how many of the search hits should be returned in the response. The default value of size is 10. If size is not specified, the response will contain 10 hits from the context under the query. Typically, if we are only interested in getting aggregation results, we should set the size to 0 to avoid getting any results along with the aggregation result. Broadly, there are three types of aggregations that Elasticsearch supports: bucket aggregations, metric aggregations, matrix aggregations. Let's start with bucket aggregations. Bucket aggregations segment the data in question, defined by the query context, into various buckets identified by the buckets key. Bucket aggregation evaluates each document in the context by deciding which bucket it falls into. At the end, bucket aggregation has a set of distinct buckets with their respective bucket keys and documents that fall into those buckets. For people who come from an SQL background, a query that has group by is doing this. This query divides the table by the different values of column 1 and returns a count of documents within each value of column 1. This is an example of bucket aggregation. The next aggregation is metric. Metric aggregations work on numeric types of fields. They compute the aggregate value of a numeric field in the given context. For example, we have a table containing the results of a student's examination. Each record contains marks obtained by the student. A metric aggregation can compute different aggregates of that numeric score column. Some examples are sum, average, minimum, maximum, and so on. In SQL terms, this query gives a rough analogy of what a metric aggregation may do. This query computes the average score in the given context. Here, the context is the whole table, that is, all students. This is an example of metric aggregation. Then we move on to matrix aggregations. Matrix aggregations were introduced with Elasticsearch version 5.0. Matrix aggregations work on multiple fields and compute matrices across all the documents within the query context. Matrix aggregations can be nested inside bucket aggregations, but bucket aggregations cannot be nested inside of matrix aggregations. This is still a relatively new feature. Coverage of matrix aggregations is not within the scope of this course. Now we will look at preparing data for analysis. We will consider an example of network traffic data generated from Wi-Fi routers. First, we will understand the structure of data. The diagram here depicts the design of the system to help you gain a better understanding of the problem and the structure of data collected. The enriched records are stored in Elasticsearch in a flat data structure. Let's look at what one record looks like. So I will create a file and show you. This is the record. One record contains various metrics for the given end client device at the given time. First is the customer to which the Wi-Fi router and device belongs to. Then access point ID is the identifier of the Wi-Fi router or access point. Time of the record is in milliseconds since epoch January the 1st, 1970. Then we have MAC address of the client device and name of the user to whom the device is assigned. Department is of the user to which the device belongs to. Then application name or domain name for which traffic is reported. Category of the application is news. Network ID contains SSID of the network. Band is 5 GHz or 2.4 GHz. Location has latitude and longitude separated by comma. Upload total is bytes uploaded since the last report. Download total is bytes downloaded since the last report. Usage is total bytes downloaded and uploaded in a current period. Upload current is upload speed in bytes per second in current period. Download current is download speed in bytes per second in current period. Bandwidth is total speed in bytes per second, upload speed plus download speed. Signal strength is the strength between Wi-Fi router and device. Now that we know what our data represents and what each record represents, let's load the data in our local instance. Please make sure that Logstash is installed. One more thing we need to do is unzip the network_traffic_data.zip file, which should create a file network_traffic_data.json file in the same directory. You can see the files here. In the JSON file, you can see a large amount of records. After that, we have to update the conf file and ensure that it has the correct path of the JSON file. Then we create the index by executing this command in the Kibana console. Execute this command. You can see an exception that the resource already exists. If you do it for the first time, you will get an acknowledgement with value true. As I am executing it for the second time, I get this exception. Now, navigate to your command line and enter the path where conf file is placed. Execute this command. The process of data importing has started, and it will take some time as the data record is very big. After you have imported the data, verify that your data is imported with this query. You should see a response like this. Now that we have the data that we want, we can get started with learning about different types of aggregations. We will learn different types of aggregations on the data that we just loaded. The next video will be about metric aggregations. Let's begin with the video Metric Aggregations. Metric aggregations work with numeric data, computing one or more aggregate metrics within the given context. The context could be a query, filter, or no query to include the whole index or type. Metric aggregations can also be nested inside other bucket aggregations. In this case, these metrics will be computed for each bucket in the bucket aggregations. We will learn about the sum, average, min, and max aggregations. Let us learn them one by one. We will start with sum, average, min, and max aggregations. Finding the sum of a field, the minimum value for a field, the maximum value for a field, or an average are very common operations. For the people who are familiar with SQL, query to find the sum would look like this. This query will calculate the sum of the download total field across all records in the table. This requires going through all records of the table or all records in the given context and adding the values of the given fields. In Elasticsearch, a similar query can be written using the sum aggregation. Let us understand the sum aggregation first. Here is how to write a simple sum aggregation. The ags or aggregations element at the top level should wrap any aggregation. Give a name to the aggregation. Here we are doing the sum aggregation on the download total field, and hence the name we chose is download_sum. You can name it anything. This field will be useful while looking up this particular aggregation's result in the response. We are doing a sum aggregation, hence the sum element. We want to do term aggregation on the download total field. Specify size as 0 to prevent raw search results from being returned. We just want aggregation results and not the search results in this case. Execute this and the response should look like this. The response should look like this. Let us understand the key aspects of the response. The key parts are numbered 1, 2, 3, and so on. The hits.total element shows the number of documents that were considered or were in the context of the query. If there was no additional query or filter specified, it will include all documents in the type or index. Just like the request, this response is wrapped inside aggregations to indicate as such. The response of the aggregation requested by us was named download_sum, hence we get our response from the sum aggregation inside an element with the same name. Value is the actual value after applying the sum aggregation. The average, min, and max aggregations are very similar. Let's look at them briefly. The average aggregation finds an average across all documents in the querying context. This is the query. The only notable differences from the sum aggregation are that we chose a different name, download_average, to make it apparent that the aggregation is trying to compute the average. The type of aggregation that we are doing is AVG instead of the sum aggregation that we were doing earlier. We will execute it. The response structure is identical, but the value field will now represent the average of the requested field. The min and max aggregations are exactly the same. Here is how we will find the minimum value of the download total field in the entire index or type. Let's finally look at max aggregation also. Here is how we will find the maximum value of the download total field in the entire index or type. These aggregations were really simple. In the next video, we will perform bucketing on string and numeric data. Hi, welcome to the next video, bucketing on string and numeric data. We will start with string data. The most common way to bucket or segment your string-typed data is by using terms aggregation. Let us take a look at terms aggregation. We are interested in the most served categories, not in terms of bandwidth used, but just in terms of counts, record counts. In a relational database, we could write a query like this. The Elasticsearch aggregation query, which would do a similar job, can be written like this. Let us understand the terms of the aggregation query here. The ags or aggregations element at the top level should wrap any aggregation. Give a name to the aggregation. Here we are doing term aggregation by the category field, and hence the name we chose is by category. We are doing a term aggregation, hence the element terms. We want to do a term aggregation on the category field. Specify size as 0 to prevent raw search results from being returned. We just want aggregation results and not the search results in this case. Execute it. The response looks like this. The total element under hits, we will refer to this as hits.total navigating the path from the top JSON element, is 252,000. This is the number of total documents considered in this aggregation. The hits.hits array is empty. This is because we specified size as 0 so as not to include any search hits here. What we were interested in were the aggregations and not search results. The aggregations element at the top level in the JSON response contains all the aggregation results. The name of the aggregation is by category. This is the name that was given by us to this term aggregation. This name helps us relate the response to the request, as the request can be generated for several aggregations at once. doc_count_error_upper_bound is the measure of error while doing this aggregation. sum_other_doc_count is the total count of documents that are not included in the buckets returned. By default, term aggregations return the top 10 buckets if there are more than 10 distinct buckets. The remaining documents other than these 10 buckets are summed and returned in this field. In this case, there are only 8 categories, and hence this field is set to 0. Next is the list of buckets returned by the aggregation. The key of one of the buckets, that is, the category of chat, the count of documents in the bucket. As we can see, there are only 8 distinct buckets in the results of the query. Next, we want to find out the top applications in terms of the maximum number of records for each application. Notice how we have added size as 0 as a request parameter in the URL itself. This returns a response like this one. Notice the sum_other_doc_count has a big value, 134,864. This is a big number relative to the total hits. As we saw in the previous query, there are around 252,000 documents in the index. The reason for this is that term aggregation returns only 10 buckets by default. The number in sum_other_doc_count is the sum of the counts for the remaining 20 applications which were not included in the buckets list. To get the top n buckets instead of the default 10, we can use the size parameter inside the term aggregation. Notice that this size, specified inside the terms aggregation, is different from the size specified at the top level. At the top level, the size parameter is to prevent any search hits, whereas the size inside the term aggregation denotes the maximum number of term buckets to be returned. Term aggregation is very useful for generating data for pie charts or bar charts, where we may want to analyze the relative counts of string-typed field in a set of documents. Execute and observe the response. Next, we will look at how to do bucketing on numeric types of fields. We will look at 2 aggregations in this section: histogram aggregation and range aggregation. Histogram aggregation can slice the data into different buckets based on one numeric field. The range of each slice, also called the interval, can be specified in the input of the query. We have records of network traffic usage data. The usage field has the number of bytes used for uploading or downloading data. Let us try to divide or slice all the data based on the usage. This aggregation query will slice all the data into different buckets. 0 to 999. All records that have usage greater than or equal to 0 and less than 1000 will fall into this bucket. 1000 to 1999. All records that have usage greater than or equal to 1000 and less than 2000 will fall into this bucket. 2000 to 2999. All records that have usage greater than or equal to 2000 and less than 3000 will fall into this bucket. And so on. The response should look like this. This is how the histogram aggregation creates buckets of equal ranges by using the interval specified in the query. By default, it includes all buckets with the given interval regardless of whether there are any documents in that bucket or not. Let us look at another aggregation, range aggregation, which can be used on numeric data. What if we do not want all buckets to have the same interval? It is possible to create unequal-sized buckets by using range aggregation. Enter this query. This aggregation slices the data into 3 buckets, up to 1 kilobyte, 1 kilobyte to 100 kilobytes, and 100 kilobytes or more. Notice that we can specify from and to in the ranges. Both from and to are optional in the range. If only to is specified, that bucket includes all documents up to the specified value in that bucket. The to value is exclusive and is not included in the current bucket's range. The response of this request looks like this. It is possible to specify custom key labels for the range buckets. The resulting buckets will have the keys set with each bucket. This is helpful for looking up the relevant bucket from the response without iterating through all buckets. Next, we will understand a couple of important concepts related to bucket aggregation and aggregations in general. Then we perform aggregations on filtered data. Let us revisit the example that we looked at in the terms aggregation section. We found out the top categories in the whole index and type. Now what we want to do is to find the top category for a specific customer and not for all the data for all customers. We modified the original query, which found the top categories, with an additional query. We added a query, and inside that query, we added a term filter for a specific customer that we were interested in. The hits total element in the response is now much less than the earlier aggregation query, which was run on the whole index and type. We may additionally want to apply more filters to limit the query to a smaller time window. This query applies multiple filters and makes the scope of the aggregation more specific, for a customer and within some subset of the time interval. Execute this query. This is how the scope of aggregation can be modified by using filters. We will continue on our detour of learning about different bucket aggregations, and look at how to nest metric aggregations inside bucket aggregations. Let us understand this by taking a question that we may want to get an answer for. What is the total bandwidth consumed by each user or a specific customer on a given day? We have to take some steps. Let's look at the query. First, filter the overall data for the given customer and for the given day. This can be done using a global query element of the bool type. Once we have filtered the data, we want to create some buckets per user. Once we have one bucket for each user, we want to compute the sum metric aggregation on the total usage field, which includes upload and download. The thing to notice here is that the top level by_users aggregation, which is a terms aggregation, contains another aggs element with the metric aggregation total_usage inside it. The response should look like this. As you can see, each of the term aggregation buckets contains a total_. Usage child, which has the metric aggregation value. The buckets are sorted by the number of documents, in each bucket in descending order. It is possible to change the order of buckets by specifying the order parameter within the bucket aggregation. Bucket aggregations can be nested inside other bucket aggregations. Let us understand this by getting an answer to this question. Who are the top 2 users in each department, given the total bandwidth consumed by each user? This query will help us get that answer. Query filters the specific customer and time range. By departments is the top-level terms aggregation to get a bucket for each department. By_users is the second-level terms aggregation to get the top 2 users. Notice size equals 2 within each bucket. Order sorts the bucket using the total_usage nested aggregation in descending order. Total usage is the metric aggregation that has the sum of usage within its parent bucket. The immediate parent bucket of the total_usage aggregation is the by_users aggregation, which causes the sum of usage to be calculated for each user. This is how we can nest bucket and metric aggregations to answer complex questions in a very fast and efficient way about big data stored in Elasticsearch. We conclude this course here. In the next video, we will perform bucketing on date and time data. Hello everyone. We have reached the fourth video of the section, bucketing on time and date data. We have seen how to bucket or segment or slice your data on different types of columns or fields. The analysis of data across the time dimension is another very common requirement. Elasticsearch has a very powerful date histogram aggregation. Using date histogram aggregation, we will see how to first create buckets on a date field. In the process, we will go through creating buckets across time periods, using a different time zone, computing other metrics within sliced time intervals, and focusing on a specific day and changing intervals. Starting with creating buckets across time. Enter this query. This query will slice the data into intervals of 1 day. Just like how we are able to create buckets on different values of strings, the following query will create buckets on different values of time, grouping it by 1-day intervals. We have specified size as 0 as a request parameter instead of specifying it in the request body. We are using the date_histogram aggregation. We want to slice the data by day. That's why we specify the interval for slicing the data as 1D for 1 day. Intervals can take values like 1D, 1 day, 1H, 1 hour, 4H, 4 hour, 30M, 30 minutes, and so on. This gives tremendous flexibility when specifying a dynamic criteria. The response to the request should look like this. As you can see, the simulated data that we have in our index is only for a 3-day period. The returned buckets contain keys in 2 forms, key_as_string and key. The key field is milliseconds since the epoch, January 1st, 1970, and key_as_string is the beginning of the time interval in UTC. In our case, we have chosen the interval of 1 day. The first bucket with this key is the bucket that has documents between September 23rd, 2017 UTC and September 24th, 2017 UTC. Now we will use a different time zone. We actually want to slice the data by IST time zone rather than slicing it according to the UTC time zone. This is possible by specifying the time_zone parameter. We need to separate the offset of the required time zone from the UTC time zone. In this case, we need to provide +530 as the offset, as IST is 5 hours and 30 minutes ahead of UTC. Execute this. The response now looks like this. As you can see, the key and key_as_string for all buckets have changed. The keys are now at the beginning of the day in the IST time zone. There are no documents for September the 24th, 2017 now, as it is a Sunday. Further, we will compute other metrics within sliced time intervals. So far, we have just sliced the data across time by using the date histogram to create the buckets on the time field. This gave us document counts in each bucket. Next, we will try to answer the question, what is the day-wise total bandwidth usage for a given customer? This query will provide us precisely that. We added a term filter to consider only one customer's data. Within the date_histogram aggregation, we nested another metric aggregation, sum aggregation, to count the sum of the usage field within each bucket. This is how we will get the total data consumed each day. The response of the query can be seen here. Next, we will see how to focus on a specific day by filtering the data for the other time periods and changing the value of the interval to a smaller value. We are trying to get an hourly breakdown of data usage on September 25th, 2017. It's also called drilling down in the data. Often, the result of the previous query is displayed as a line chart with time on the x-axis and data used on the y-axis. If we want to zoom in on a specific day from that line chart, this query is useful. Execute this query. The response would look like this. As you can see, now we have buckets for 1 hour intervals with data for those hours aggregated within each bucket. Cool! We end this video here. In the next video, we will perform bucketing on geospatial data. Welcome to the next video, bucketing on geospatial data. We will cover two types of geospatial aggregations, geodistance aggregation and geohash grid aggregation. Geodistance aggregation helps in creating buckets of distances from a given geopoint. This is better understood using a diagram. The shaded area in blue represents the area included in the geodistance aggregation. Enter this query. This aggregation will form a bucket with all the documents within the given distance from the given geopoint. As you can see, the ranges parameter is similar to the range aggregation that we saw earlier. It includes all the points up to 5 meters away from the given origin specified. This is helpful in aggregations such as getting the count of things that are within 2 kilometers from a given location, and is often used on many websites. The default unit of distance is meters, but you can specify the unit parameter as kilometers or mile and others to switch to different units. Execute this and observe the corresponding response. Now let's look at what happens if you specify both from and to in the geodistance aggregation. Here we are bucketing the points which are at least 5 meters away but less than 10 meters away from the given point. Similarly, it is possible to form a bucket of a point which is at least x units away from the given origin by specifying only the from parameter. Execute this and compare the response with the previous one. Let us look at geohash grid aggregation. Geohash grid aggregation uses the geohash mechanism to divide the map into smaller units. You can read about geohash at this link. The geohash system divides the world map into a grid of rectangular regions of different precisions. Lower values of precision represent larger geographical areas, and higher values represent smaller, more precise geographical areas. Enter the next query. The data that we have in our network traffic example is spread over a very small geographical area, so we have used a precision of 7. The supported values for precision are from 1 to 12. Let us look at the response to this request. This is the response. After aggregating the data onto geohash blocks of precision 7, all the documents fell into 2 geohash regions, with the respective document counts seen in the response. We can zoom in on this map or request the data to be aggregated on smaller hashes by increasing the value of the precision. When you try a precision value of 9, you will see this response. As you can see, the geohash grid aggregation can allow you to slice or aggregate the data over geographical regions of different sizes or precisions, which is quite powerful. On this note, we conclude this section. The next section is about building data pipelines with Logstash. Hello guys, welcome to another exciting section of the course, Building Data Pipelines with Logstash. One of the important processes of Logstash is converting unstructured log data into structured data, which helps in searching for relevant information easily and also assists in analysis. Now we will move on to the first video of this section that deals with parsing and enriching logs using Logstash. The analysis of structured data is easier and helps us find meaningful or deeper analysis, rather than trying to perform analysis on unstructured data. Most analysis tools depend on structured data. Kibana, which we will be making use of for analysis and visualization, can be used effectively if the data in Elasticsearch is right. Log data is typically made up of two parts, as shown on the screen. Here, timestamp is the time when the event occurred, and data is the information about the event. Data may contain just a single piece of information, or it may contain many pieces of information. Let us look at the need for Logstash. We would need to have a mechanism for extracting this information from the data, and thus converting the unstructured data or event into a structured data or event. This is where the filter section of the Logstash pipeline comes in handy. The filter section is made up of one or more filter plugins that assist in parsing and enriching the log data. Let's look at the functions of filter plugins. A filter plugin is used to perform transformations on the data. It allows us to combine one or more plugins, and the order of the plugins defines the order in which the data is transformed. A sample filter section in Logstash pipeline would look like this. The generated event from the input plugin goes through each of the plugins defined in the filter section, during which it transforms the event based on the plugins defined. Finally, it is sent to the output plugin to send the event to the appropriate destination. Let's explore some common filter plugins used for transformation. We will start with the first plugin, that is, CSV filter. This filter is useful for parsing .csv files. This plugin takes the event containing CSV data, parses it, and stores it as individual fields. Let's take some sample data and use a CSV filter to parse data out of it. So we will create a new file and name it as users.csv. In this file, we will store this sample data. This code block shows the usage of the CSV filter plugin. The CSV plugin has no required parameters. It scans each row of data and uses default column names such as column 1, column 2, and so on to place the data. This plugin by default uses a comma as a field separator. The default separator can be changed by using the separator parameter of the plugin. One can either specify the list of column names using the columns parameter, which accepts an array of column names, or by using the autoDetect_column_names parameter set to true. In doing so, one can let the plugin know that it needs to detect the column names automatically. So, we will create another file and name it as csvfile.conf. Here, we will add this code snippet implementing the configuration. As you can see here, we are using autoDetect_column_names parameter and set it to true. Lastly, we will save both the files. After that, using command prompt, we will navigate to the directory where we have stored the csvfile.conf file and this logstash command to display the data within the file. Grab a cup of coffee, as it may take some time to complete its execution. This is result of the data saved in the users.csv file that we created previously. If you remember, we had used autoDetect_column_name parameter in the csv_file conf. In the generated output, you can see that the column names are detected automatically. Lastly, we will terminate the job. Next is mutate filter. This filter allows one to perform general mutations on fields. One can rename, convert, strip, and modify fields in the events. Let's enhance the csvfile.conf file that we created previously with the mutate filter and understand its usage. In the csv_file.conf, we will replace the existing code with this big block of code to show the use of the mutate filter. This part of the code is the main change, as here we are defining the mutate function. Here, the convert setting within the filter helps to change the data type of a field. The valid conversion targets are integer, string, float, and boolean. The rename setting within the filter helps to rename one or more fields. The preceding example renames the fname field to first name and lname to last name. Next is the G subsettings. It is used to match a regular expression against a field value and replace all matches with a replacement string. As regular expressions work only on strings, this field can only take a field containing string or an array of strings. It takes an array consisting of 3 elements per substitution, that is, it takes the field name, regex, and the replacement string. For example, dot in the email ID field is replaced with underscore. This strip settings is used to strip the leading and trailing white spaces. Uppercase is used to convert the string to uppercase. In the preceding example, the value in the gender field is converted to uppercase. Similarly, by using various settings of the mutate filter, such as lowercase, update, replace, join, and merge, one can lowercase a string, update an existing field, replace the value of a field, join an array of values, or merge fields. Before moving ahead, save this file. Switch to the command prompt and view the output. To view the updated content of the csv_file.conf file, we will execute this command. Wait patiently, as it may take some time to complete the execution. Once it's done, you will see this output with necessary changes that we made in the file. Lastly, we will terminate the batch job. Now, let us understand what is grok filter. This is a powerful and often used plugin for parsing the unstructured data into structured data, thus making the data easily queryable or filterable. In simple terms, grok is a way of matching a line against a pattern, which is based on a regular expression, and mapping specific parts of the line to dedicated fields. The general syntax of a grok pattern is as it is displayed on the screen. Pattern is the name of the pattern that will match the text. The field name is the identifier for the piece of text being matched. By default, groked fields are strings. To cast either to float or int values, one can use this format. Logstash ships with about 120 patterns by default. These patterns are reusable and extensible. Also, patterns consist of a label and a regex. An example is shown on the screen. It can also contain other patterns. If a pattern is not available, then one can use a regular expression using this format. For example, the regex would match telephone numbers, such as 123, 123, 1234, and place the parsed value into the phone field. Let's look at some examples to understand grok better. Similar to the previous examples, we will create a new file and name it as grok1.conf. Here we will add this code snippet and understand the code in detail. If the input line is of the format shown in the overlay, then the output will be generated as this code snippet. There is a tool hosted on this website which helps one to build grok patterns that match the log. Further, we will move on to the next type of filter, date filter. This plugin is used for parsing the date from the fields. This plugin is very handy and useful when working with time series events. By default, Logstash adds a at the rate timestamp field for each event, representing the time it processed the event. But the user might be interested in the actual timestamp of the generated event rather than the process timestamp. So, using this filter, one can parse the date or timestamp from the fields and then use it as the timestamp of the event. Let's create a new file and name it as basic_datefilter.txt file. Here we will show that how this plugin can be used. By default, the date filter overwrites the timestamp field, but this can be changed by providing an explicit target field. So let's add it here. Thus, the user can keep the event time processed by Logstash too. Then, if the time field has multiple possible time formats, then those can be specified as an array of values to the match parameter. You can have a look at the format here. By default, the time zone will be the server local time unless specified. To manually specify the time zone, use the time zone parameter or setting of the plugin. The valid time zone values can be found at this URL. Moving on to GeoIP filter. This plugin is used to enrich the log information. Given the IP address, it adds the geographical location of the IP address. It finds the geographical information by performing a lookup against the GeoLite2 city database for valid IP addresses and populates fields with results. GeoLite 2 City database is a product of the MaxMind organization and is available under the CCA Share Alike 4.0 license. Logstash comes bundled with GeoLite 2 City database, so when performing a lookup, it need not perform any network call, hence the lookup is fast. The only required parameter for this plugin is the source, which accepts an IP address in string format. This plugin creates a geo-IP field with geographical details such as country, postal code, region, city, and so on. A geo-IP and location field is created if the geo-IP lookup returns a latitude and longitude, and it is mapped to the geo_point type when indexing to Elasticsearch. Geo-IP_point fields can be used for Elasticsearch's geospatial query, facet, and filter functions, and can be used to generate Kibana's map visualization. The last filter type is user agent filter. This filter parses user agent strings into structured data based on browser scope data. You can learn more about it at this link. It adds information about the user agent such as family, operating system, version, device, and so on. To extract the user agent details, this filter plugin makes use of the regexes.yaml database that is bundled with Logstash. The only required parameter for this plugin is the source parameter, which accepts string containing user agent details. In the next video, we will be exploring another component of Elasticsearch, beats, and commonly used beats by Elastic Company. Hi, welcome to the last video of the section, Beats. Beats are lightweight data shippers that are installed as agents on edge servers to ship operational data to Elasticsearch. Let us take a look at some of the commonly used beats by Elastic Company. We will begin with Metric Beat. It is a lightweight shipper that periodically collects metrics from the operating system and from services running on the server. It helps one to monitor services by collecting metrics from the system and services such as Apache, MongoDB, Redis, and so on that are running on the server. Metric Beat can push the collected metrics directly into Elasticsearch or send them to Logstash, Redis, or Kafka. Next is Packet Beat. It is a real-time network packet analyzer that works by capturing the network traffic between the application servers, decoding the application layer protocols, HTTP, MySQL, Redis, Memcache, and many more, correlating the requests with the responses, and recording the interesting fields for each transaction. Let's proceed with Heartbeat. It is a new addition to the Beat ecosystem and is used to check if a service is up or not, and checks if the services are reachable. Heartbeat is a lightweight daemon that is installed on a remote server to periodically check the status of services running on the host. Heartbeat supports ICMP, TCP, and HTTP monitors for checking hosts and services. Winlog Beat is the next type of beat. It is a beat dedicated to the Windows platform. Winlog Beat is installed as a Windows service on Windows XP or later to read from one or more event log using Windows APIs. It filters the events based on user-configured criteria and then sends the event data to the configured output, such as Elasticsearch or Logstash. Also note that Winlog Beat can capture event data such as application events, hardware events, security events, and system events. Further moving with Audit Beat. That is a new addition to the Beats family, first implemented in Elastic Stack 6.0. Audit Beat is a lightweight shipper that is installed on servers to monitor user activity and processes and analyze the event data in the Elastic Stack without touching Linux's Audit-D. Audit Beat communicates directly with the Linux audit framework, collects the same data as Audit-D, and sends the events to Elastic Stack in real time. These are the beats that are developed by the open source community using the Beats framework. These are some of the open source beats along with its description. The complete list of community beats can be found at this URL. The Beats Developer Guide provides the necessary information to create a custom beat. You can find the Developer Guide at this web link. After understanding the Logstash and Beats introduction, you might get confused as to whether Beats is a replacement for Logstash, the difference between them, or when to use one over the other. Beats are lightweight agents and consume less resources, and hence are installed on the edge servers, where the operational data needs to be collected and shipped. Beats lack the powerful features of Logstash for parsing and transforming events. Logstash comes with a broad array of input, filter, and output plugins for collecting, enriching, and transforming data from a variety of sources. However, it is very resource intensive and can also be used as an independent product outside of Elastic Stack. Logstash is recommended to be installed on a dedicated server rather than edge servers and listens for incoming events for processing. We have successfully downloaded and installed Elastic Stack and Kibana to begin the journey of learning about Elastic Stack. In the next section, we will discover methods to visualize data with Kibana. Hello, welcome to the next section, Visualizing Data with Kibana. In this section, we will explore the various components of Kibana and explore how one can use it for data analysis. Let's begin this section by configuring and preparing data Kibana. As we already saw how to install Kibana, we will skip it now. Kibana is a web application, and unlike Elasticsearch and Logstash, which run on JVM, Kibana is powered by Node.js. During bootup, Kibana tries to connect to Elasticsearch running on http://localhost:9200. We saw that too. Kibana is started on the default port 5601. So, in the URL tab, change this app to status and you will be taken to the status page. The status page displays information about the server's resource usage and lists the installed plugins. Kibana should be configured to run against an Elasticsearch node of the same version. Running different patch version releases of Kibana and Elasticsearch is generally supported, but not highly encouraged. Running different major version releases of Kibana and Elasticsearch is not supported, nor is running minor versions of Kibana that are newer than the version of Elasticsearch. What if we want to change some of these settings? All the configurations of Kibana are stored in a file called kibana.yml, which is present under the folder config under kibana_home. When this file is opened in your favorite text editor, it contains many properties that are commented by default. What this means is that unless those are overridden, the value specified in the property is considered the default value. We will now look at the key configuration settings that one should look for when starting out with Kibana. First is the server.port. This setting specifies the port Kibana would be serving requests. It defaults to 5601. Next comes server.host. Specifies the address to which the Kibana server will bind. IP addresses and host names are both valid values. It defaults to localhost. Then comes elasticsearch.url, the URL of the Elasticsearch instance to use for all your queries. It defaults to http localhost 9200. If your Elasticsearch is running on a different host or port, make sure you update this property. Next is elasticsearch.username and elasticsearch.password. If Elasticsearch is secured, specify the username and password details that have access to Elasticsearch here. In the next section, XPack, we will be exploring how to secure Elasticsearch. Server.name is a human-readable display name that identifies this Kibana instance. It defaults to host name. Then comes kibana.index. Kibana uses an index in Elasticsearch Elasticsearch to store saved searches, visualizations, and dashboards. Kibana creates a new index if the index doesn't already exist. Defaults to .kibana. Note that the YML file is space sensitive or indentation aware. Make sure all the uncommented properties have the same indentation, or else an error will be thrown upon Kibana startup and it will fail to start. As Kibana is all about gaining insight from data, let's load some sample data that we will use as we move ahead. One of the most common use cases is log analysis. For this, we will load Apache server logs into Elasticsearch using Logstash, and then using it in Kibana for analysis and building visualizations. Make sure you have Logstash version 5.6 and above installed. Here, logs.gz file is placed. Also make sure that you unzip this file into your working directory. Here, create a config file named apache.conf. Here, add this code. Here, see to it that you give the proper path of logs file. Save this file. Open the command prompt and start the Logstash using this line of code. This is done so that it can begin processing the logs and index it to Elasticsearch. Logstash will take a while to start, and once it gets started, you should see a series of dots, a dot per processed log line. Let's now verify the total number of documents, log events indexed into Elasticsearch. This is the code to do it. In the response, you should see a count of 300,000. That's all for now. In the next video, we will look at Kibana UI. Hello guys, welcome back to the next video, Kibana UI. In the last video, we prepared the data. Let's begin by opening the Kibana from the browser using the URL http localhost 5601. The landing page will look like this. Let us now understand the user interaction before diving into the core components of Kibana. This is a representation of typical user interaction flow. Prior to using Kibana for data analysis, the user would have already loaded the data in Elasticsearch. In order to analyze the data using Kibana, the user has to first make Kibana aware of the data stored in ES indexes. So the user would need to configure the indexes on which he wants to perform analysis. Once configured, the user has to find out the data structure, such as the fields present in the document and the type of fields present in the document, and explore the data. This is done so that he can decide how he can visualize this, and what type of questions he wants to pose and find answers for in terms of the data. After understanding the data and having formed questions to find answers for, he would create appropriate visualizations that would help him in seeking the answers easily from huge amounts of data. The user then creates a dashboard from the set of visualizations created earlier, which would tell the story about the data. This is an iterative process, and the user would juggle around the various stages to find answers to his questions. Now that we have an idea about how the user would use Kibana and interact with it, let's understand what Kibana is made up of. As seen in the left side of the collapsible menu sidebar, the Kibana UI consists of these components: Discover, Visualize, Dashboard, Timeline, and DevTools. Before you can start working with data and creating visualizations to analyze the data, Kibana requires you to configure the index pattern. Index patterns are used to identify the Elasticsearch index, which will have search and analytics run against it. They are also used to configure fields. An index pattern is a string with optional wildcards that can match multiple indices. Typically, two types of index exist within Elasticsearch. Time series indexes. If there is a correlation between the timestamp and data, the data is called time series data. This data will have a timestamp field. Examples would be logs data, metrics data, and tweet data. Regular indexes. If the data doesn't contain any timestamp and the data has no correlation with time, then the data is called regular data. Typically, this data is stored in single indexes. For example, departments data and product catalog data. As we loaded sample data in the previous video, let's configure it so that we can make use of it for the rest of the section's examples. Click on Management in the Index Pattern field, type logstash-. For the time filter field name, select @timestamp and click Create. Once done, you will see a screen like this. Now let us look at Discover Page. Discover Page helps you to interactively explore the data. It allows the user to interactively perform search queries, filter search results, and view document data. It also allows the user to save the search or filter criteria so that it can be reused or used to create visualizations on top of the filtered results. By default, Discover Page displays the events of the last 15 minutes. Set the appropriate date range in the time filter. Navigate to Time Filter, Absolute Time Range, and set from as 2014-05-28 and 2 to 2014-07-01. Click Go. Now the Discover page contains the sections. This is the index pattern. All the configured index patterns are shown here in a drop-down, and the default one is selected automatically. The user can choose the appropriate index pattern for data exploration. This is the fields list. All the fields that are part of the document are shown in this section. Clicking on the field shows the quick count, that is, how many of the documents in the Documents table contain a particular field, what the top 5 values are, and what percentage of documents contain each value. Next is Document Table. This section shows the actual document data. The table shows the 500 most recent documents that match the user-entered query or filters sorted by timestamp. By clicking the Expand button found to the left of the Documents table entry, data can be visualized in table format or JSON format. During data exploration, we are often interested in a subset of fields rather than the whole of the document. In order to add fields to the document table, either hover over the field on the Fields list and click its Add button, or expand the document and click the field's Toggle Column in Table button. Added field columns replace the _source column in the Documents table. Field columns in the table can be shuffled by clicking the right or left arrows found when hovering over the column name. Here we cannot see it as we only have one column. So we add another column name. Now we get to see it. Similarly, when clicking the Remove button, that is the cross sign, columns can be removed from the table. This is the query bar. Using the query bar, you can enter queries to filter the search results. Submitting a search request results in the histogram being updated, and the Documents table, fields lists, and hits being updated to reflect the search results. Matching search text is highlighted in the Document table. To search your data, enter your search criteria in the query bar and press Enter, or click the search icon. The query bar accepts two types of queries: an Elasticsearch query string query, which is based on Lucene query syntax. You can learn more about it from this link. Next is full JSON-based Elasticsearch query DSL. You can visit this link to learn more about it. Elasticsearch query string provides the ability to perform various types of searches ranging from simple to complex queries that adhere to Lucene query syntax. First is free text search. To search for text present in any of the fields, simply enter a text string in the query bar. When you enter a group of words to search for, as long as the document contains any of the words or all or part of the words in any order, the document is included in search result. If you are doing an exact phrase search, that is, the documents should contain all the words given the search criteria, and the words should be in same order, then surround the phrase with quotes. For example, file logstash or files logstash. Next is field search. To search for values against a specific field, use the syntax field : followed by value and : Here we get the result. Next comes Boolean search. One can make use of Boolean operators such as and, or, and hyphen to build complex queries. Using Boolean operators, one can combine field, value, and free text as well as shown. Note that the operators and or are case sensitive. This is an example of must not match operator. And this is an example of a must not operator with a field. And this is an example of a must not operator with free text. Note that there should be no space between the hyphen operator and the search text or field. Next is grouping searches. When we want to build complex queries, often we have to group the search criteria. Grouping both by field and value is supported. First, we add another field named response. We replace this search with this new one. As you can see, we have achieved the result. Next is range search. This allows you to search within a range of values. Inclusive ranges are specified with square brackets, for example start_value to end_value, and exclusive ranges with curly brackets, for example start_value to end_value, as shown here. Ranges can be specified for dates and numeric or string fields. The to operator is case sensitive and its range values should be numeric values. Next is wildcard and regex search. By using the asterisk and question mark wildcards with search text, queries can be executed. Asterisk denotes 0 or more matches and question mark denotes 0 or 1 match. This is our example. Wildcard searches can be computationally expensive. It is always preferable to add a wildcard as a suffix rather than a prefix of the search text. Like wildcards, regex queries are supported too, by using slashes and square brackets. Regex patterns can be specified. But be cautious when using regex queries, as this is very computationally expensive. For example, search for any city starting with either G, B or A. This is the result that we get. Now we move on to Elasticsearch DSL query. By using the DSL query, queries can be performed from the query bar. The query part of the DSL query can be used to perform searches. This is an example of searching for documents that have IE in the user_agent.name and Washington in the goip.region_name field. Also remove this field. You can see the result. Now we move to hits. Hits represent the total number of documents that match the user-inputted query or criteria. Then comes histogram. This section is only visible if a time field is configured for the selected index pattern. This section displays the distribution of documents over time in a histogram. By default, the best time interval for generating the histogram is automatically inferred based on the time set in the time filter. However, the histogram interval can be changed by selecting the interval from the drop-down. During data exploration, the user can slice and dice through the histogram and filter the search results. Hovering over the histogram converts the mouse pointer to a plus symbol. When left-clicking, the user can draw a rectangle to inspect or filter the documents that fall in those selected intervals. Now we move to Toolbar. User-entered search queries and applied filters can be saved so that they can be reused or used to build visualizations on top of the filtered search results. The toolbar provides options for saving, reusing, and sharing the search queries. The user can refer to existing stored searches later and modify the query, and can either overwrite the existing search or save it as a new search by checking the Save as New Search checkbox in the Save window. First, create a new search based on an existing saved search. Clicking the Open button displays the saved searches. In Kibana, the state of the current page or UI is stored in the URL itself, thus allowing it to be easily shareable. Clicking the Share button allows you to share the saved search. Now we move to Time Picker. This section is only visible if a time field is configured for the selected index pattern. The time filter restricts the search results to a specific time period, thus assisting in analyzing the data belonging to the period of interest. When the Discover page is opened, by default the time filter is set to the last 15 minutes. Time Filter provides the few options to select the time periods. Click on Time Filter to access the options. Quick Time Filter helps you to filter quickly based on some already available time ranges. Relative Time Filter option helps you to filter based on the relative time with respect to the current time. Relative times can be in the past or the future. A checkbox is provided to round the time. Absolute time filter helps you to filter based on inputted start and end times. Next is auto refresh. During the analysis of real-time data or data that is continuously generated, a feature to automatically fetch the latest data would be very useful. Auto refresh provides such a functionality. By default, refresh interval is turned off. The user can choose the appropriate refresh interval that assists this analysis. Now we move to filters. By using positive filters, one can refine the search results to display only those documents that contain a particular value in a field. One can also create negative filters that exclude documents that contain the specified field value. Let us look at an example. We open this up. This is a positive filter and this is a negative one. One can add field filters from the fields list or the documents table and even manually add a filter. In addition to creating positive and negative filters, the documents table enables one to filter whether or not a field is present. To add a positive or negative filter, in the fields list or documents table, click on the positive icon or negative icon respectively. Similarly, to filter a search through whether or not a field is present, click on the asterisk icon. Exists filter. One can also add filters manually by clicking the Add a Filter button found below the query bar. Clicking on the button will launch a pop-up in which filters can be specified and applied by clicking the Save button. This is a positive filter. The applied filters are shown below the query bar. Negative filters are shown in red. One can add multiple filters, and we will look at some actions that can be applied on the applied filters. Enable or disable filter. Allows the enabling, disabling of the filter without removing it. Diagonal stripes indicate that a filter is disabled. Pin filter. Pins the filter. Pinned filters persist when you switch contexts in Kibana. For example, you can pin a filter in Discover and it remains in place when you switch to the Visualize or Dashboard page. Toggle filter. Allows you to switch from a positive filter to a negative filter and vice versa. Remove filter allows you to remove the applied filter. Edit filter allows you to edit the applied filter. With that, we complete a part of Kibana UI. In the next video, we will learn about Visualize. Hi, welcome back to the next video, Visualize. In the last video, we learned about Kibana UI. Now we continue further. The Visualize page helps to create visualizations in the form of graphs, tables, and charts, thus assisting in visualizing all the data that has been stored in Elasticsearch easily. By creating visualizations, the user can easily make sense of data and can obtain answers to the questions that might have formed during the data discovery process. These built visualizations can be used when building dashboards. All visualizations in Kibana are based on the aggregation queries of Elasticsearch. Aggregations provide the multidimensional grouping of results. Kibana supports two types of aggregations: bucket aggregations, metric aggregations. As aggregation concepts are key to understanding how visualizations are built, let's get an overview of it before jumping into building visualizations. The grouping of documents by a common criteria is called bucketing. Bucketing is very similar to the group by functionality in SQL. Depending on the aggregation type, each bucket is associated with a criterion which determines whether or not a document in the current context belongs to the bucket or not. Each bucket provides the information about the total number of documents it contains. Bucket aggregations, given an employee index containing employee documents, find the number of employees based on their age, group, or location. Given the Apache Access Logs index, find the number of 404 responses by country. Bucket aggregation supports sub-aggregations. That is, given a bucket, all the documents present in the given bucket can be further bucketed, grouped based on criteria. For example, finding the number of 404 responses by country and also by state. Kibana supports the following types of bucket aggregations: histogram, date histogram, range, terms, filters, and geohash grid. This is used to compute metrics based on values extracted from the fields of the document. Metrics are used in conjunction with buckets. The different metrics that are available are count, average sum, median, min, max, standard deviation, percentiles, and percentile ranks. Creating a visualization. There are some steps to create visualizations. First, navigate to the Visualize page and click the Create a New Visualization button or the plus button. Then select a visualization type. We select Pie. Then select a data source. Finally build the visualizations. The Visualize interface looks like this. The components of the Visualize interface are Visualization Designer. This is used for choosing appropriate metrics and buckets for creating visualizations. Visualization Preview. Based on the metrics, buckets, queries, filters, and time frame selected, the visualization is dynamically changed. The next is Spy Panel. This allows you to inspect raw Elasticsearch requests, responses, tabular data, and HTTP request statistics. Query bar field filters is used to filter the search results. Label reflects the metric type and bucket keys as labels. Colors in the visualization can be changed by clicking on Label and choosing the color from the color palette. Toolbar Time Filter provides the option to save or share the visualizations. Also, using the time filter, the user can restrict the time to filter the search results. Let us take a look at each visualization type in detail. Line, area, and bar charts. These charts are used for visualizing the data distribution by plotting it against an XY axis. These charts are also used for visualizing the time series data to analyze trends. Data table. This is used to display aggregated data in a tabular format. Markdown widget. This visualization is used to create formatted text containing general information, comments, and instructions pertaining to a dashboard. Metric. Metric aggregations work only on numeric fields and display a single numeric value for the aggregations that are selected. Goal. Goal is a metric aggregation that provides visualizations that display how the metric progresses towards a fixed goal. Gauge. A gauge is a metric aggregation which provides visualizations that are used to show how a metric value relates to the predefined thresholds or ranges. Pie charts. This visualization is used to represent part-to-whole relationships. Parts are represented by slices in the visualization. Coordinate maps. This visualization is used to display the geographical area mapped to the data determined by the specified buckets or aggregations. Region maps. Region maps are thematic maps in which boundary vector shapes are colored using a gradient. Tag cloud. A tag cloud is a visual representation of text data typically used to visualize free-form text. So, in the next video, we will see how different visualizations can help us. Now we move on to the next video, Visualization in Action. Let's see how different visualizations can help us in doing these tasks. Analyzing the response codes over time. Finding the top 10 URLs requested. Analyzing the bandwidth usage of the top 5 countries over time. Finding the most used user agent. Analyzing the web traffic originating from different countries. First, we will go for response codes over time. This can be visualized easily using a bar graph. So, for this, we will create a new visualization. First, go to the Visualize page and click on the Create a Visualization button. Then, from the basic chart options, select Vertical Bar. After this, below the field, from a new search, select Index, select Logstash. Now, in the X-axis, select Date Histogram and for field, choose Timestamp. Once done, click on Add Sub-Buckets and choose Split Series. Select Terms as the sub-aggregation and Response.keyword as the field. And lastly, click the Play button, that is, we apply changes. You can now see the output. Cool! Now, save the visualization as response codes by time. As seen in the visualization, there is a significant amount of 404. Now, to analyze just the 404 events, from the Labels or Keys panel, click on 404 and then click Positive Filter. We can now see the resulting graph. You can expand the Labels keys and choose the colors from the color palette and thus change the colors in the visualization. Pin the filter and navigate to the Discover page to see the requests resulting in 404s. Now, let's see the top 10 URLs requested. This can be visualized easily using a data table. For this, first create a new visualization. Click on the plus icon. For visualization type, select Data Table. Select Logstash under From a New Search. After that, select Buckets, type as the split rows, and select Aggregation as the terms. Following that, select the Request.keyword field. Also set the size to 10. And finally, now click the Play button. Also, we save the visualization as top 10 URLs. Note that custom label fields can be used to provide meaningful names to the aggregated results. Most of the visualizations support custom labels. Data table visualizations can be exported as a .csv file by clicking raw or formatted links found under the data table visualization. So, now we are ready to see the bandwidth usage of top 5 countries over time. To demonstrate this, let's go to the visualization page and first create a new visualization by clicking on the plus icon and select Area Chart. Then select Logstash under From a New Search, select Index. In Y-axis, select Aggregation Type as the sum and Bytes as the field. Similarly, in X-axis, select Date Histogram and @Timestamp as the field. Now click Add Sub-Buckets and select Split Series. After that, select Terms as the sub-aggregation, and now select the field. Finally, click the Play button. You can now see the output display. Don't forget to save the visualization as top 5 countries by bandwidth usage. Let us now check the web traffic originating from different countries. This can be visualized easily using a coordinate map. Create a new visualization and select Coordinate Map. Then select Logstash under From a New Search, select Index. Set the bucket type to geo-coordinates and select the aggregation as geo-hash. After this, select the geo-ip.location field. Now, in the Options tab, select Map Type as Heat Map, and finally, click the Play button. Save the visualization as Traffic by Country. For the same visualization, if the metric is changed to bytes, you can see the change in the resulting visualization. You can click on the plus or minus button found at the top left of the map and zoom in or zoom out. There's one more interesting fact that we can check in the map that is most used user agent. This can be visualized easily using a variety of charts. Let's use Tag Cloud. Go to Visualize page and create a new visualization. After this, select Tag Cloud and choose Logstash under From a New Search, select Index. Next, set the bucket type to tags and select the terms aggregation. Also select the useragent.name.keyword field. Set the size to 10 and click the play button. Superb! save the visualization as most used user agent. You can notice that Chrome, followed by Firefox, is the user agent the majority of traffic is originating from. That's all for this video. In the next video, we will be working with dashboards. We are back with a new video, Dashboards. Dashboards help one bring different visualizations into a single page. By using the previously stored visualizations and saved queries, one can build a dashboard that tells a story about the data. Let's see how we can build a dashboard for our log analysis use case. In order to create a new dashboard, navigate to the dashboard page and click the Create a Dashboard button or the plus button. On the resulting page, you can click the Add button, which shows all the stored visualizations and saved searches that are available to be added. Clicking on the saved search visualizations will result in them getting added to the page. Further, you can edit, rearrange, expand, or remove the visualizations using the buttons available at the top corner of each visualization. Once the required visualizations are added to the dashboard, make sure to save the dashboard by clicking the Save button available in the toolbar and provide a title. When a dashboard is saved, all the query criteria and filters get saved too. If you want to save the time filters, then while saving the dashboard, select the Store Time with Dashboard checkbox. We have not selected it here in our case. Saving the time along with the dashboard might be useful when you want to share or reopen the dashboard in its current state. Now, let us see how we could clone the dashboard. So, using the clone feature, you can copy the current dashboard, along with its queries and filters, and create a new dashboard. For example, you might want to create new dashboards for continents or countries. To clone the dashboard, click on the Clone tab at the top, and for the clone dashboard, give a name, say Traffic Dashboard Copy, and click on Confirm Clone. So, we have successfully created a clone of our dashboard. OK. We can also share the dashboard. Using the Share feature, you can either share a direct link to a Kibana dashboard with another user, or embed the dashboard in a web page as an iframe. That's all for now. Up next, we will explore about Timeline and plugins. We have reached the last video of this section, Timeline and plugins. Timeline is a visualization tool for analyzing time series data in Kibana. It enables you to combine totally independent data sources within the same visualization. Using its simple expression language, you can execute advanced mathematical calculations, such as dividing and subtracting metrics, calculating derivatives and moving averages, and visualizing the results of these calculations. Timeline is present in the left pane of the Kibana UI, between the dashboard and DevTools icons, so click on it. The main component or feature of the Timeline UI is the Timeline query bar, where I have placed the cursor. This allows one to define expressions that influence the generation of the graphs. It allows one to define multiple expressions separated by commas, and also allows you to chain functions. The Timeline UI also offers the few amazing options. Let's explore them one by one. First is New. This is used to create a new Timeline sheet for creating graphs. Next, Add. One can create multiple charts on the same Timeline sheet using this option. Save is used to save the timeline page. It provides two options, which are to save the timeline sheet or save the current expression as a Kibana dashboard panel. And Open is used to open the existing saved timeline sheet. Then we have Options. This provides the option of specifying the number of rows and columns in the timeline sheet. Next is Help. This provides the documentation for starting out with Timeline and also provides the documentation for all the supported functions in Timeline expressions. The last one, Time Filter. This provides the time filter options for filtering the data. Now, the simplest timeline expression used for generating graphs is the one which you see highlighted on your screen. Timeline expressions always start with a dot followed by the function name which can accept one or more parameters. The .es asterisk expression queries data from all the indexes present in Elasticsearch. By default, it will just count the number of documents, resulting in a graph showing the number of documents over time. If you'd like to restrict Timeline to data within a specific index, for example, Logstash, you can specify the index within the function, as I have done here. As Timeline is a time series visualizer, it uses the @timestamp field present in the index as the time field for plotting the values on an x-axis. One can change it by passing the appropriate time field as a value to the time field parameter. Timeline's helpful auto-completion feature will help you build the expression as you go along. Let's see some examples in action to understand Timeline better. We'll start by working on the time filter. So, navigate to Time Filter and select the absolute time range to set the appropriate date range in the time filter. Here we set from as 28th of May 2014 at midnight and to the 1st of July at midnight. Now click Go. Let's find the average bytes usage over time for the US. And here's the expression for this. So, this is how the output should look like. Now, Timeline allows for the plotting of multiple graphs in the same chart as well. By separating the expressions with commas, one can plot multiple graphs. Let's find the average bytes usage over time for the US and the average bytes usage over time for China. In the Timeline query bar, add these expressions. We can now observe the average bytes usage for both the countries. Timeline also allows for the chaining of functions. Let's change the label and color of these graphs. For this purpose, add these expressions in the timeline query bar. Click on the play button to see the output. Nice! One more useful option in Timeline is using offsets to analyze old data. This is useful for comparing current trends with earlier patterns. Let's compare the sum of bytes usage over the previous week for the US. The expression for this would be these two lines. Note that this output demonstrates the ability to add multiple charts to the same timeline sheet. By clicking the Add button, one can add multiple charts. Selecting the chart changes the associated expression in the Timeline query bar. Timeline also supports the pulling of data from external data sources using a public API. Timeline has a native API for pulling data from the World Bank, Quandl, and Graphite. Now we will move ahead to work with plugins. Plugins are a way to enhance the functionality of Kibana. All the plugins that are installed will be placed under the Kibana home directory. Elastic, the company behind Kibana, provides many plugins that can be installed, and there are quite a number of public plugins that are not maintained by Elastic which can be installed too. Now, to install plugins, navigate to Kibana home directory and execute the install command to install any plugins. During installation, either the name of the plugin can be given if it's hosted by Elastic itself, or the URL of the location where the plugin is hosted can also be given. For example, to install Xpack, a plugin developed and maintained by Elastic, execute the command bin/kibana-plugin.bat install x-pack. It may take a few seconds. Done. Since we already have it installed on our machine, we got the message that plugin Xpack already exists. Now, to remove a plugin, navigate to Kibana home directory and execute the remove command followed by the plugin name. So the Xpack plugin is successfully removed. In this section, we covered how to effectively use Kibana to build beautiful dashboards for effective storytelling about your data. Also, we learned how to configure Kibana to visualize data from Elasticsearch, and we looked at how to add custom plugins to Kibana. In the next section, we will cover Elasticsearch and the core components that help when building data pipelines. We will also cover visualizing data to add the extensions needed for specific use cases. Hello everyone, welcome to the last section of the course, Building a Sensor Data Analytics Application. In this section, we will build one such application using Elasticstack that can handle a large amount of data applying the techniques that we have learned so far. Now we will move on to the first video of this section that deals with modeling data in Elasticsearch. We have seen the structure of the final record after enriching the data. That should help us model the data in Elasticsearch. In this video, we will apply few techniques to model the data. Techniques such as defining an index template, understanding the mapping. Let us look at the index template that we will define. In the Kibana console, click on DevTools to navigate to the console. Here, we will execute this code snippet. This index template will create a new index with the name sensor data with year-month-date format when any client attempts to index the first record in this index. On executing the code, we will get this output. Another technique is understanding the mapping. The mapping that we defined in the index template contains all the fields that will be present in the denormalized record after lookup. Moving on to setting up the metadata database. We need to have a database that has metadata about the sensors. This database will hold the tables that we discussed in the introduction to the application section. We are storing the data in a relational database, MySQL, but you can use any other relational database equally as well. Since we are using MySQL, we will be using the MySQL JDBC driver to connect to the database. Please ensure that you have a few things set up on your system. First, we need to have MySQL database community version 5.5, 5.6, or 5.7. You can use an existing database if you already have it on your system. Another important thing is to install the downloaded MySQL database and log in with the root user. In our case, we have already downloaded and installed MySQL database and logged in with our root user. After that, we will execute this block of code. You can view the result in the output section at the bottom. Last task that we need to perform is log in to the newly created sensor metadata database and verify that the three tables, those are sensor type, locations, and sensors, exist in the database. You can verify that the database was created and populated successfully by executing this query. On executing this query, we will get this result. You can observe that our sensor metadata database is ready to look up the necessary sensor metadata. In the next video, we will build the Logstash data pipeline. Hi friends, welcome to the next video of the section, Building the Logstash Data Pipeline. Having set up the mechanism to automatically create the Elasticsearch index and also the metadata database, we can now focus on building the data pipeline using Logstash. Let's explore about what should our data pipeline do. The answer is it should perform a few steps, such as accept JSON requests over the web, that is, over HTTP. Enrich the JSON with the metadata we have in the MySQL database. Store the resulting documents in Elasticsearch. These three main functions that we want to perform correspond exactly to the Logstash data pipeline's input, filter, and output plugins respectively. Let's look at how to achieve the end goal of our data pipeline by these aforementioned steps. We will start with accepting JSON requests over the web, over HTTP. Before starting with the example, we will first see how does it function in short. This function is achieved by the input plugin. Logstash has support for the HTTP input plugin, which does precisely that. It builds an HTTP interface using different types of payloads that can be submitted to Logstash as an input. Let's have a look at a working example. First, we will create a new file and name it as logstash-sensor-data-http.conf. In this file, we will add the relevant part that has the input filter. Here, the ID field is a string that can uniquely identify this input filter later in the file if needed. We will not need to reference this name in the file. We just chose a name sensor data HTTP input. Documentation of the HTTP input plugin is available here at this link. In this instance, since we are using the default configuration of the HTTP input plugin, we have just specified ID. We will secure this HTTP endpoint as it will be exposed over the internet to allow sensors to send data from anywhere. Then we will add these two lines that will configure user and password to protect this endpoint with the desired username and password. After that, when Logstash is started with this input plugin, it starts an HTTP server on port 8080, which is secured using basic authentication with the given username and password. So you command prompt navigate to it properly. In the command prompt, we will specify the path location of logstash sensor data http.conf file by executing this command. Navigating to your favorite browser and run localhost 8080. When you will log in for the first time, you will be asked to enter your credentials. As you can see, we have successfully received the OK message. Then we will open another command prompt. Here we will execute a curl command to send a request to this Logstash pipeline. On executing this command, we will receive exactly the same message as an output. Let us proceed and see how we will enrich the JSON with the metadata we have in the MySQL database. The enrichment and other processing part of the data pipeline can be done using filter plugins. We have built a relational database that contains the tables and the necessary lookup data for enriching the incoming JSON requests. Logstash has a JDBC streaming filter plugin that can be used to do lookups from any relational database and enrich the incoming JSON documents. Let us look into the filter plugin section in our Logstash configuration file. We will add this big block of code in the configuration file. As you will notice, there are two filter plugins used in the file. JDBC streaming, mutate. Let us see what each filter plugin is doing. We will begin with JDBC streaming plugin. We essentially specify the whereabouts of the database that we want to connect to, username or password, JDBC driver, .jar file, and class. Initially, we need to download the latest MySQL JDBC driver, also known as Connector J, from this web link. Then we will download the .tar or .zip file containing the driver and extract it into your system. The path of this extracted .jar file should be updated in the JDBC driver library parameter. As you can see, we have updated the path in the configuration jar file. To summarize, you should review and update the parameters in the Logstash configuration to point to your database and driver jar file. So, the parameters are JDBC driver library, JDBC connection string, JDBC password. The statement parameter has the same SQL query that we saw earlier. It looks up the metadata for the given sensor_ID. A successful query will fetch all additional fields for that sensor_ID. The result of the lookup query is stored in a new field, lookupResult, as specified by the target parameter. Going further, we will use the mutate filter plugin to modify this JSON to the desired end result that we want in Elasticsearch. Further, we will see how the mutate filter plugin achieves certain objectives. The first objective is, it moves the looked up fields that are under lookupResult directly in JSON. As we have seen, lookupResult is an array with just one element, the element at index 0 in the array. We need to move all the fields under this array element directly under the JSON payload. This is done field by field using the rename operation. For example, this operation renames the existing sensor type field directly under the JSON payload. We do this for all the looked up fields that are returned by the SQL query. Next, it combines the latitude and longitude fields under lookupResult as a location field. This is achieved by using the add field operation to construct the location field. By now, we should have a new field called location added to our JSON payload, exactly as desired. Next, we will remove the undesirable fields. After moving all the elements from the lookupResult field directly in the JSON, we don't need that field anymore. Similarly, we don't want to store the headers and the host fields in the Elasticsearch index. So, we remove them all at once using this operation. By now, we would have the JSON payload in the structure that we want in the Elasticsearch index. Next, let us see how to send it to Elasticsearch. Firstly, store the resulting documents in Elasticsearch. We will use the Elasticsearch output plugin that comes with Logstash to send data to Elasticsearch. The usage is very simple. We just need to have Elasticsearch under the output tag as highlighted in the code. Here we have specified hosts and index to send the data to the right index within the right cluster. Notice that the index name will be specified in this format. Remember that we had defined an index template with the index pattern sensor data. When the first event on 1st December 2017 is sent, the output plugin defined here will send the event to index sensor data as 2017.12.01. Further, if we want to send events to a secured Elasticsearch cluster, we can configure the user and password as displayed here. This way, we will have one index for every day, where each day's data will be stored within its index. Now that we have our Logstash data pipeline ready, let's send some data. So, we will send data to Logstash over HTTP. At this point, sensors can start sending their readings to the Logstash data pipeline that we have created in the previous section. They just need to send data using this curl command. Since we don't have real sensors, we will simulate the data by sending these types of requests. The simulated data and script that sends this data are incorporated in the code that is placed in the code bundle. As you can see, this is the data folder path. Further, make sure that you have git bash downloaded and installed in your system. If you don't have git bash, please download and install Git for Windows from its official website. In our case, we have already downloaded and installed it on our system. Next, let's go to the data directory and execute this command. Automatically bin bash window will be opened and it will read the sensor data.json line by line and submit to Logstash using the curl command. We have just played 1 day's worth of sensor readings, taken every minute from different sensors across a few geographical locations to Logstash. The Logstash data pipeline that we had built earlier should have enriched and sent the data to our Elasticsearch. It is time to switch over to Kibana and get some insights from the data. In the next video, we will be visualizing the data in Kibana. Hi, welcome to the last video of the section, Visualizing the Data in Kibana. We have successfully set up the Logstash data pipeline and also loaded some data using the pipeline into Elasticsearch. It is time to explore the data and build a dashboard that will help us gain some insights into the data. Let's start by doing a sanity check to see if the data is loaded correctly. We can do so by going to Kibana DevTools and executing this query. This query will search data across all indices matching the sensor_data pattern. There should be a good number of records in the index if the data was indexed correctly. You can see this is the total number of records that were indexed. Going forward, we will cover topics such as set up an index pattern in Kibana, build visualizations, create a dashboard using the visualizations. Let us initiate with the first step, set up an index pattern in Kibana. Before we can start building visualizations, we need to set up the index pattern for all indexes that we will potentially have for the sensor data analytics application. We need to do this because our index names are dynamic. We will have one index per day, but we want to be able to create visualizations and dashboards that will work across multiple indices of sensor data, even when there are multiple indices. To do this, we will go to the Management tab on Kibana and click on the Index Patterns link. Here we will click on the Create Index Pattern button and add the sensor_data index pattern. Then in Time Filter field name, choose the time field in the Time Filter field name as time and finally click on Create an Index Pattern button. Great! We have successfully created the index pattern for our sensor data. Next, we will start building some visualizations. Before we embark on an analytics project, we often already have some questions that we want to get answered quickly from visualizations. We will also start with some questions and try to build visualizations to get answers to those questions. We will try to answer the questions such as, how does the average temperature change over time? How does the average humidity change over time? How do temperature and humidity change at each location over time? Can I visualize temperature and humidity over a map? How are the sensors distributed across departments? Let us build visualizations to get the answers, starting with the first question. Here, we are just looking for an aggregate statistic. We want to know the average temperature across all temperature sensors, regardless of their location or any other criteria. As we saw in Section 6, Visualizing Data with Kibana, we will go to the Visualize tab to create new visualizations and click on the button with a plus sign. Here we will choose Basic Charts and then select the Line Chart item. To configure the line chart, we will perform 5 easy steps. So first, click on the small clock icon at the top right corner, choose Absolute and select the date range as 1st December 2017 to 2nd of December 2017. We have to do this because our simulated sensor data is from the 1st of December 2017. Then click on Add a filter as shown in figure 10.8. Choose the filter as sensor type as temperature and click on the Save button. We have two types of sensors, temperature and humidity. In the current visualization that we are building, we are only interested in the temperature readings. This is why we've added this filter. From the Metrics section, choose the values as shown in figure 10.8. We are interested in the average value of the readings. We will enter the label to be average temperature. After that, from the Buckets section, choose the date histogram aggregation and the time field with the other options left as the same. Lastly, click on the triangular Apply Changes button. The result is the average temperature across all temperature sensors over the selected time period. As you can see here, this is what we were looking for when we started building this visualization. From this graph, we can quickly see that on the 1st of December 2017, at 15 IST, the temperature became unusually high. The time may be different on your machine. We may want to find out which underlying sensors reported higher than normal temperatures that caused this peak. We can click on the Save link at the top bar and give this visualization a name. Let's call it Average Temperature Over Time. Later, we will use this visualization in a dashboard. Let us proceed to the next question, which is similar to the previous question. Here the question is, how does the average humidity change over time? We can reuse the previous visualization, make a slight modification, and create another copy to answer this question. We will start by opening the first visualization, which we saved with the name Average Temperature Over Time. Hover on the filter with label center, type Temperature, and click on the edit icon as you can see here. Then we will change the filter value from temperature to humidity and click on Save. Also, modify custom label from average temperature to average humidity and click on the Apply Changes button. As you will see, the chart is updated for the humidity sensors. You can click on the Save link at the top navigation bar and give a new name to the visualization as Average Humidity Over Time. Check the Save as a new visualization box and click on Save. This completes our second visualization and answers our second question. Proceeding with the next question, that is, how do temperature and humidity change at each location over time? This time, we are looking to get more details than the first two questions. We want to know how the temperature and humidity vary at each location over time. We will solve it for temperature. So, we will navigate to the Visualizations tab in Kibana and create a new line chart visualization, the same as how we did before. We will add a filter for sensor type as temperature. Then set the metrics section to do average aggregation on the reading field. And select custom label as average temperature. Under the bucket section, choose X-axis. Since we are aggregating the data over the time field, we need to choose the date histogram aggregation. Here, we will choose the time field and leave the aggregation interval to be auto. Up to this point, this visualization is the same as average temperature over time. We don't just want to see the average temperature over time, we want to see it per location. On floor, which is our most fine-grained unit of identifying a location. This is why we are splitting the series using terms aggregation on the field location on floor in this step. Post that, we select Order By to be metric, average temperature, and keep 5 as the order size to keep only the top 5 locations. We have now built a visualization that shows how the temperature changes for each value of location on floor in our data. By clicking on the Apply Changes button, you will clearly see that there is a spike in 0201 on the 1st of December 2017 at 1500 IST. Because of this spike, we had seen the average temperature in our first visualization spike at that time. This is an important insight that we have uncovered. A visualization for humidity can be created by following the same steps, but just replacing temperature with humidity. Moving on to the next question. Can I visualize temperature and humidity over a map? Let's visualize temperature and humidity over the map using the coordinate map visualization. To create a new coordinate map visualization, we will perform certain steps. As in previous visualizations, add a filter for sensor type temperature and click on Save button. In the metrics section, choose average aggregation on the reading field. Enter the custom label as average temperature. Since this is a coordinate map, we need to choose the geohash grid aggregation and then select the geo_point field that we have in our data. Location is the field to aggregate. After making all the changes, click on the Apply Changes button. As you can see, it helps in visualizing our data on the map. We can immediately see the average temperature at each site when we hover over a specific location. Focus on the relevant part of the map and save the visualization with the name Temperature over Locations. You can create a similar coordinate map visualization for the humidity sensors. Going ahead, what if we want to see how the sensors distributed across different departments? Remember, we have the department field in our data, which we had got after enriching the data using the sensor_ID. Pie charts are particularly useful to visualize how data is distributed across multiple values of a keyword type of field, such as department. We will start by creating a new pie chart visualization. We will perform a few steps to create a visualization for locations across departments. For that, select the Sensor Data Index. In the Metrics section, we will choose Unique Count Aggregation and Location on Floor field. Then enter the custom label as Number of Locations. Next, in the Buckets section, select the bucket type as Split Slice. Also, we need to choose Terms Aggregation on the Department field as we want to aggregate the data across different departments. Here, the Order By field remains the same. Modify the size to 10. Click on Apply Changes and save this visualization as Locations across departments. You can also create another similar visualization to visualize locations across different buildings. Let us build a dashboard from the visualizations that we have created so far. For that, click on the Dashboard tab from the left-hand side navigation bar in Kibana. Then click on the plus button to create a new dashboard. At the top, click on Add Menu Bar item to add visualizations to your newly created dashboard. As you click, you will see all the visualizations we have built in a drop-down selection. You can add all the visualizations one by one. Further, we can drag or resize to create a dashboard that suits our requirements. Now we will see what a dashboard may look like for the application that we are building. With Dashboard, we can add filters by clicking on the Add a Filter link near the top left corner of the dashboard. The selected filter will be applied to all the charts. The visualizations are interactive. For example, clicking on one of the pies of the donut charts will apply that filter globally. Let's see how it can be helpful. Here, we will click on the Add a Filter link and add the building name as 222 Broadway. As we save, we will see the filter for building name 222 Broadway added to the filters. This will allow us to see all of the data from the perspective of all the sensors in that building. Let us delete that filter by hovering over the building name 222 Broadway filter and clicking on the trash icon. Next, we will try to interact with one of the line charts, that is, the average humidity over time visualization. As we observed earlier, there was a spike on the 1st of December 2017 at 1500 IST. It is possible to zoom into a particular time period by clicking, dragging and drawing a rectangle around the time interval that we want to zoom into within any line chart. In other words, just draw a rectangle around the spike, dragging your mouse while it is clicked. The result is that the time filter applied on the entire dashboard, which is displayed in the top right corner, is changed. This concludes our application and demonstration of what we can do using the Elastic Stack components. With this, we have reached the end of our course. I am confident that this course would have given you all the basic learnings about ELK and its applications. Thank you for being with us. Wishing you all the best. Keep practicing, keep coding. See you in the next course.